Welcome to the Theoretical Neuroscience Podcast. I am the host, Gaute Einvoll. There are many types of mathematical modeling used in neuroscience. In mechanistic or physics-type modeling, models are constructed based on the properties of the building blocks of the system one is interested in. An example here is the celebrated Hodgkin-Huxley model, where action potential generation in neurons is explained based on various types of ions passing through the cell membrane. Another example is cortical network models built by connecting numerous neurons, as was discussed in podcast number 4 with Sasha van Albeda. In descriptive or statistical modeling, we instead start with experimental recordings and try to extract insights directly from them. With the advent of experimental methods that allow for the recording of spikes from many neurons simultaneously, lots of different statistical methods have been developed and used to analyze such many neuron data. If we think of the activity of each neuron as a component of a vector, the firing activity of 3 neurons can be thought of as a vector in 3-dimensional space with 3 components, while the activity of 100 neurons can be thought of as a vector in 100-dimensional space. One popular method for exploring such high-dimensional data is PCA, or Principal Components Analysis. The mathematical subfield of topology offers another way to analyze such high-dimensional data. Topology is said to be geometry without distances, and the topology of a donut is equivalent to a coffee mug since both have one and only one hole. Today's guest, Carina Curto, is one of the pioneers in the application of topological methods in the analysis of neural data. She was trained as a physicist and did string theory, one of the most mathematical branches in physics, before switching to neuroscience. She is now a professor of mathematics at Brown University. In the podcast, we talk about what topology is, and in particular how it can be used in an analysis of neural data. For people that are new to topology, which includes me and I guess many of the listeners, there are quite a few new ideas and concepts introduced in the podcast, like homology, cliques, Bethe curves, and Rips complexes. This is at times a bit heavy going for newcomers, but I think Carina does an excellent job in explaining this complicated material. Further, for people who want to dive deeper into it, I link to several papers and some other material she has produced on the episode homepage. In a completely different kind of work, Carina has also studied simplified network models, and this work follows in the tradition of the influential work by John Hopfield in the 1980s, where he studied simplified network models, beautifully displaying principles for how so-called attractor memories may work. The model studied by Hopfield had so-called symmetric connectivity, meaning that the connections between any pairs of 2 neurons in the network were the same. This assures that memory states in the network are stable. Carina's work considers networks with asymmetric connectivity, and then the dynamics of the network becomes much richer and, for example, displays limit cycles corresponding to oscillatory network activity. While the analysis of such networks are more difficult than for the Hopfield network, Carina and colleagues are, as we talk about in the podcast, still able to extract nice principled qualitative insights about how this rich dynamics comes about. As for all episodes, information about the episode and relevant links can be found at the webpage theoreticalneuroscience.no. If you want to support the podcast, go to patreon.com/theoreticalneurosciencepodcast and choose a membership of your liking, for example, at the cost of $1 per month. As a member, you will get access to a video version of the podcast recording, as well as transcripts of each episode. And note that there is a 7-day free trial period when you sign up. I also have a YouTube channel called Theoretical Neuroscience Podcast, where you can watch the videos as well. I will be most grateful if you become a Patreon supporter to help me fund the production of the podcast, even if you're not too interested in looking at the videos. But I also appreciate all the other listeners, and I hope that all of you can help spread the word about the podcast to other people in the community, on social media or otherwise. Okay, here is Carina. Welcome to the podcast, Carina Curto.
Thank you. Thanks for having me.
Today's podcast is about the use of topological methods in neuroscience. At least the first part is about that. So, what is topology?
All right. So, topology is an area of mathematics that started probably about 100 years ago.
Mm,
And it's really it's kind of a study of shape and geometry, but without distances.
mm,
So, you're looking at properties of shapes that don't have to do with angles or
mm,
precise distances in any way.
mm. I can sort of understand that it's sort of an interesting topic from like a mathematics point of view, but it's as we discussed earlier, it doesn't sound too powerful to be able to just tell. I don't know, not to disparage the field. We'll come to some cool applications, but it doesn't sound too powerful to begin with.
Well, it's yeah, so maybe you can tell me a little more about why you think that.
Well, I mean, if you sort of as if you sort of like a donut and a coffee cup are
Mhm.
topologically equivalent, right? But
Right.
I would say that in many aspects, a donut and a coffee cup are very different, which is not captured by topology. So that
Right.
sort of it just
Yeah.
seems to group together a lot of things which are quite different.
Yeah. So that is true. You certainly don't want to eat a coffee cup and try to out of a donut.
No?
It is true that I think that's sort of the canonical example that's used, right?
Yeah.
To kind of so that it hits home how extreme it is, the kind of information topology throws away. Um, but at the same time, sometimes you really want to throw information away. Sometimes that's sort of the point. You want to sort of look for features that are invariant
Mm,
under distances changing, under morphing. So,
mm,
for example, um, well, okay, I mean, maybe I'll back up a little bit. I should say that it's the power of topology is not that it demands that you throw away geometry. So you can
no.
use geometric methods with topological methods. And in fact,
Mm,
some of the most powerful work combines the two. It's that it looks specifically for features that you won't necessarily see if you're just looking at distances and metrics.
mm,
And it highlights different aspects of the shape.
mm. And this like there's something called algebraic topology, which is a subfield of mathematics.
Yeah.
So what is algebraic topology?
Yes, I would say when mathematicians say topology, they usually, not always, but they usually mean algebraic topology. And
Mm,
so this is actually the machinery, the tools
mm,
for detecting these properties. So when you go back to the donut and the coffee cup, the key feature there is that they both have a hole in them,
mm.
right? So in the coffee cup, it's in the not in my coffee cup, interestingly,
Okay.
which has no which
Okay.
has no handle, right?
No,
But the idea is that
exactly.
it's the
Mine
handle.
has like
Yours
this is
does, right? So
yeah.
yours
Yeah.
does. And
Mm,
then the donut, if it not
yeah.
all donuts have holes in them, but a classic donut has a
Mm,
hole in it. Um, and so that's kind of the feature. Now the question is, if you look at that by eye, you can see the hole, right? But if you're given a description of the shape in some other way, how do you detect that, right? So how can you use mathematics and use equations and algebra to detect that? So in the same way that say if you're looking at the graph of a function and you want to detect the zeros, if you
mm,
can plot it, right, and you can see, oh, there's a zero here, there's a zero here, right, but you can also do algebra, right, and solve for when the equation equals zero and find the zeros. And so
mm,
algebraic topology is an algebraic way
mm.
of detecting those holes.
And you I think learned topology first in the context of like some quantum mechanics and some didn't you some
Um,
like string theory, Calabi-Yau manifolds and
yeah. So I okay. So I was a physicist by training.
mm,
So I did my undergraduate degree at Harvard in physics, and then, but I was very into mathematics as well, and then
mm,
I wanted to do string theory. So
mm.
it's true that I went to graduate school to do string theory, but I actually went to a math department to do this
Okay,
because string
yeah.
theory was then and still is, a very mathematical
Mm,
area of physics, and so So I would say I learned topology. Well, I took kind of an undergrad topology class already at Harvard, sort of
Okay.
in when I was an undergraduate, and that was a basic point set topology, the fundamental group. So a little bit of an introduction to algebraic topology, but not much. And then I took algebraic topology my first year in graduate school, and I was, of course, motivated by the knowledge that this is useful in theoretical physics,
Mm.
and not just string theory. So topological ideas are useful, actually, quite broadly in physics.
Mm.
Um, but I should say the course I took was a standard first
Mm.
year graduate course in algebraic topology. I took a couple of semesters of it,
Mm.
and then I was,
So,
of
but
course,
you studied physics, and so you were attracted to this, like the rigor of the mathematics. Because when I was a physics student, I took one course in sort of like purish mathematics in
mhm.
some functional analysis, and I didn't have the temper for it. I got sort of a little bit annoyed by proving things that were obvious. I just would have just so. But you were maybe attracted to this,
I liked it. Yeah,
yeah.
I was attracted to this, which is sort of why I ended up, in string theory. It's not the best area of physics to go into, but if
Well,
you're attracted by, mathematics, it's
uh,
it's it's natural.
uh,
Yeah, I was attracted by this. I really liked it. I thought in
mm,
many ways, so every physicist has a different story, right? But there's certainly some of us who find the rigor of mathematics, in some sense, a little easier to deal with,
mm,
cleaner. You're relying less on, I don't know, physics intuition or whatever that is,
yeah.
right? Um, so it can make things seem
But
simpler.
then, nevertheless, you made this quite bold move over to a quite messy field of science, neuroscience. So how did that
Yes,
happen? It was like a
yes.
momentary lapse of reason, or whatever they say. Yeah.
Yeah, so that was kind of it was kind of yeah, so I did my PhD in mathematical physics and mathematical
Mm,
string theory. I studied Calabi-Yau's. I was doing algebraic geometry
mm,
of Calabi-Yau's, resolution of singularities, this kind of thing. Um, Again, motivated by string theory. And then I did make this sort of crazy move into
mm,
neuroscience. And I think the reason is because at that point, like, my PhD thesis is basically straight math.
mm,
Um, so of course it was all motivated by kind of questions in string theory, but at the end of the day, I was just doing algebraic geometry,
mm,
and that had never been my intention.
mm.
Right. So I was attracted by math. I wanted to
Okay,
learn more math.
but
I was excited.
it was too much of a good thing.
I was excited about the idea of,
Yeah.
learning algebraic topology and representation theory and,
Mm,
Riemann surfaces and all these like lovely areas of mathematics that I knew were applicable in physics, right?
mm,
And so it was still kind of like the idea that I would apply it in physics was part of what made it attractive.
mm,
And then, yeah, when I got sort of deep into, what I was doing as a string theorist, it I felt like I was kind of losing the connection to science, or to a science that felt, accessible or exciting, or that it was kind of going somewhere. Um,
mm.
so yeah, so then I made this pretty dramatic decision,
Yeah.
when I was like 25, 26 years old, to just
Mm.
that I would
Well,
finish
that's
my PhD. I was like, I'm
yeah.
gonna finish because I was in too deep, and I had a nice thesis project. I actually very much enjoyed my
Mm.
thesis project, and so I was happy to finish that. But then I thought I need to do something
Okay. Well,
else. Yeah,
20s are tough. That's when you have to make all your life-changing
yeah.
decisions, right? That's with
Yeah,
many
I feel
ways.
like I went through like a quarter life crisis or something, like around age
I see.
25, right? Yeah.
But what specifically did you do then to get into neuroscience?
Well, I actually thought I would have to do another PhD.
Mm,
And I was sort of mentally preparing myself for that, because I did get very excited about neuroscience in my last couple of years of graduate school. I started attending seminars. I took a course. I
mm,
audited an undergraduate neuroscience course, which was very exciting,
mm.
because I had sort of avoided biology for a
Really?
long
Yeah.
time, and then
Ah.
there's all this new stuff, right? So it's kind of like learning a new language, and so I kind of prepared myself, right, to make this switch. But I thought I would have to go to graduate school again, And so I was kind of delighted when I met Ken Harris,
Mm.
um, who at the time was still an assistant professor at Rutgers. So he had just started his lab. He had been a postdoc with Yuri Buzhaki, also at
Mm.
Rutgers. They've both since moved, so they're not there anymore.
Mm.
But at the time, he was recruiting. You know, he had started a lab. He had gotten some big grants.
Mm.
He had money, and his own background as an undergrad was in math. I think in Cambridge. He's British,
Mm.
um, and then he has gone to graduate school initially to do string theory, also
Really?
at Rutgers. And then, but
Okay, I
he
see.
abandoned that sort of earlier. He kind of
Uh,
came to his senses earlier,
uh,
and started and transitioned to neuroscience and ended up getting a
uh,
PhD in something kind of
uh,
different. Um,
uh,
but he was maybe one of the few one of the few computational neuroscientists at the time who was starting a lab and was actually interested in recruiting people with my background
yeah,
because it
yeah.
was so similar to his background.
That's true.
Um,
So it's not too many people who have this. I would say, like, I mean, the typical theoreticians who come into neuroscience are maybe more like physicists because, like, the mathematicians are, yeah, there are fewer of those. Like Ken Harris is one
I
of
think,
those.
yeah, I think so. So Ken, yeah. So I mean, I think the route he sort of was kind of a physics route also, but it was a string theory
Yeah.
route. So I think there are maybe fewer. I mean, maybe more now because string
Mm.
theory is sort of a, a
Mm.
difficult field to be in. So it just
Mm.
there's sort of
Yeah, but
um,
Ken Harris even started doing experiments, right? And or at least he worked on spike sorting and
he did,
yeah,
yeah, he
so he
worked
was
on
quite
spike
close to
sorting and so on.
experiments.
Yeah,
Mm.
he worked very, and he still does work very,
Yeah.
very closely to
Mm.
experiments.
Yeah.
And so he was a great mentor for me to have
Mm.
as a postdoc because I was new to the field. I really didn't know anything.
Mm.
He kind of understood what I knew and didn't know because he sort of understood my background. But he also is just, really, really great at data analysis.
Mm.
And so I feel like I learned a lot
So
about.
he helped you maybe formulate the problem. I remember when I switched to neuroscience, this thing of having a
Mhm.
neuroscientist sort of helped me to formulate the first problem to get started, sort of.
Yeah, I think he was very, yeah, and also he just sort of not just me but his whole lab. I mean, he was able to teach us uh, kind of how to do science rigorously, um, even though it's not like proof based math,
Mm.
right? And so I think that was very important because actually my background was in theoretical physics and mathematics, and of course I had this physics background, so I wasn't like totally naive to how science works. But at the
Mm.
same time, the math training, um, especially the pure math training, which is essentially the kind of math training that I had was pure math training. Um, it's it lacks something when it comes to scientific rigor.
Mm.
So pure mathematics, it's all you have this like super high standard of rigor, right? Like you
Mm.
believe a statement when you can prove it
Mm.
because proof is this all or nothing standard. Um, when you don't have a proof, I feel like as students, we're not really trained to evaluate the quality
Yeah.
the quality of a statement, right? Like, I mean, there are conjectures and people sort of believe them or not, so there's this
Mm.
sense that it's really all or nothing. It's like you don't believe something until you can prove it.
Mm.
And so then when it comes to analyzing data,
Yeah.
right, or analyzing results from an experiment, there is very little training in how do you do that rigorously? How do
Mm.
you do proper controls? It's like,
Yeah.
well, you can't prove it, so
I think
you
that
list your
applies to not only mathematics, but also most brand. At least I wasn't trained in that in physics.
Mhm.
Maybe modern physics educations have more of this, I would say, applied data analysis kind of things.
Yeah,
But
maybe. Yeah, I think if you're in a data analysis field, if you're
like,
maybe,
yeah,
computational cosmologist or something, you are trained
yeah,
more in this. But
yeah,
yeah, in theoretical physics, I didn't get much of this training
no,
either. And
no,
and it is really interesting because I struggle with this with my own graduate students. So
mm,
I'm in a math department right now, so I've had graduate students primarily coming from math, and
mm,
interested in areas
yeah,
like topology, and so they tend to have more of a pure math training. And it is tricky because they're either hyper skeptical or
yeah.
hyper gullible.
You
It's like
know,
either it's
because
like it's
I,
all bad, because
yeah,
nothing is proven,
but yeah,
or you just right? And there isn't this sense of like,
Yeah.
this is
But
good science.
but
They
I,
did all the checks they could do. They did all the
yeah,
controls they could do,
yeah,
right? I mean, there are papers that are more rigorous than others, and so
absolutely.
I
Yeah.
think, uh, yeah, one of the things I
But I
appreciate.
still think this is very hard. I mean, I struggle with myself. I think sort of
Mhm.
how
It
to
is.
trust experimental data and sort of what to when can you sort of say that I actually believe this result and when is it? Yeah, I think it's tough, right?
It is tough, and it's not right. There's not a clear line, which
No,
is what makes it tough, right? But
mm,
at the same time, I feel like there's a scientific maturity, right? So
absolutely.
and there's you definitely read papers where yes, they did. You think, oh, but did they check for this? And then the
Mm,
next paragraph is like, you
mm.
know, to
Yeah,
understand whether this was a result of some trivial
yeah,
effect, we did this control and that
yeah,
control, and
yeah.
so you have
No,
this
that's
sense of
certainly
like,
true. No, that's
right?
certainly true. And the best papers are like this,
The
right?
best
That
papers
is,
are like that. They think
yeah.
of all the things, all
Mm,
the alternative explanations, and
mm,
check for them so that they can trust their own interpretation of the
mm,
data. And I think that's a kind
mm,
of rigor that is very, very
mm.
different from what you would learn, as a math student.
So do you read a lot of experimental papers in your lab or your
I
group?
do, I do,
Yeah,
yeah, and I find and it is kind of challenging
yeah,
um, to do
yeah,
that with students
yeah.
because it is a completely new way of reading for them.
Yeah. How do and I'm sort of curious about this because I mean, so how do you do it with when you have new mathematics students coming into your lab who knows very little about biology and neuroscience and neurobiology? So do you have some kind of introductory package or something you think of?
Yeah, I mean, I do. I try. I keep sort of changing it up because
Mm,
I haven't. I don't feel like I've quite found something
mm,
that works for everybody. But yeah, I do. Recommend certain papers. Like there are sort of
mm,
classic computational neuroscience papers or experimental papers that are very relevant
mm,
for theorists. There are some books. I like
mm.
to get them to read. I actually I give as a gift to many. I sort of gave as a gift to all the students and postdocs in my lab. This is an old book, but Sebastian Sung's Connectome book
Okay,
from
yeah.
from
Hmm.
many years ago, just because I
Yeah.
thought that was a very nice introduction to the history of the
Hmm.
field and leading up to kind of the modern questions in neuroscience.
Hmm.
So
Yeah.
I like to have them read things like that. So I don't know. I mean, I do a variety of things,
Mm.
but it is challenging and it is a very different way of thinking. I think the students who have a background also in physics have an easier time.
Mm.
When they don't even have a background in physics,
Yeah,
then
no, I think that's true.
it can be
Because
really hard.
I think some people, because I've collaborated with mathematicians,
Mhm.
and some it has sort of been fruitful, but I see also some of it is what they call collaboration through the mailbox. So we sort of send in equations and we sort of get solutions out. And I don't think that's that's the most
You just
efficient.
you're able to do that. You just send equations to a mathematician, and they'll
Yeah,
just
to the mail. Oh well, I sort of a joke, but they're sort of just someone that just only interested in the equations and how to solve them,
uh-huh,
and they are not really interested in where they come from and the
where they come
consequences.
from.
Yeah,
Yeah.
but I think that's a bit it's like the many ways to be many. Yeah, and I mean many many things you can be interested. People are different, also in
People
science,
are
right?
different. Yeah,
Yeah,
people are different. So
yeah,
I definitely think mathematicians have a lot to contribute.
mm,
But it's in different ways, right? So
mm,
some people will become very interested in the science. Some people
yeah,
maybe are only interested in the math questions, and
uh,
that's maybe okay, right? So
yeah,
maybe we can
yeah,
pick aside some math questions
mm,
and send them off and see if
yeah.
we can,
See if we can get
can be
something.
solved, right?
Yeah, yeah.
Yeah.
So that's, but I mean, I can sort of use still your, so one talk you gave had sort of something about 10 theorems or something. So you
Oh,
like theorems. So I thought she's a mathematician. She's sort of,
I do. I do
yeah,
like
that's sort
theorems.
of
Yeah.
like a big difference between, I think, the theoretical physics culture and the mathematics culture. This is at least my part of like
Mhm.
more by complex system kind of where like string theory is maybe special because it's so mathematical,
And string theorists like theorems too.
mm,
But yeah, I don't know. I mean, I like when one is able to prove something about a model, right? And
yeah,
then try to think about what that means.
yeah.
So that's kind of the space I like
No,
to.
I agree. It is sort of like it's very satisfactory when something is really proven, and you don't
Hmm.
have to worry about it anymore because
Hmm.
it's it's
Hmm.
proven. That's
Yeah.
I
I mean,
certainly
what happens most often is in order to prove a theorem, you have to simplify,
of
beyond
course.
where you wanted to, right? So you have
Yeah.
to simplify a bit too much,
Yeah.
and then you can prove something. But then on
Yeah.
the other hand, that gives you kind of an idea. Well, maybe this phenomenon is true more generally, right? And then you can do
Yeah. And often
simulations or
yeah, exactly.
computational work and sort of
Yeah.
and push it. And sometimes you realize the proof
Mm.
is true more generally, or you can
Yeah.
extend it.
Yeah.
But oftentimes it's like it's one sort of corner to work in. I feel
That's
like,
right.
you know,
And I guess that also is like the theoretical physics culture is that you want to simplify things, right?
right.
And maybe, but then we say that we don't do rigorous with an R proof, we do vigorous with V. So it's sort of a vigorous proof is it probably must be true. So
Yeah.
anyway, yeah,
No, but I mean, I definitely learned that style from my theoretical physics training, because I
yeah,
remember like being in, say, quantum field theory class, and
yeah,
it was like quantum field theory is very sort of difficult mathematics, right? And
mm,
so the exercises were like, okay, imagine a universe where there's one kind of particle and it's a boson, and here's and it interacts in this way, and like,
yeah,
and then you can actually, do
yeah,
a calculation,
yeah,
right?
mm,
Right, and then then when you get to QCD, you have to like resort to computational
yeah, yeah.
tools. Yeah.
Cool. Yeah. So, but anyway, there are back to the like. There's several reasons for use of topology in neuroscience. I think starting with you had one paper, I think in 2008, where you said something that it's something about topology is a natural tool for understanding the neural code,
Yes.
right? And you had this example from. I mean, a big thing. I mean, we started with the correlation matrices, right?
So in that paper, I think we just started with like population vectors
Okay.
and
Okay.
reading
So
off
what is
points
just let's start with a population vector. That's sort of like so you have a bunch of say firing rates for
for
different
different
neurons,
neurons. I think
and
I think our
then
example was place fields.
okay.
If we're thinking about the same paper, the example was place fields. So you
Mm,
have neurons that are responsive to position and space,
mm,
and then you maybe have, say, 70 place fields,
mm,
70 place cells. Each of them has a place field. They
mm,
cover an environment, and then you
mm.
can look at the population vectors.
Okay.
So
Good.
in different time windows, you can just see which neurons fired in the same
Mm,
time window.
yeah. So then you
Okay,
get to say like if you have 70 neurons, you get a 70-dimensional
right,
like vector, and then you
right,
have these firing rates of all these neurons, and
and
then
then
without knowing anything, then you can and then
so then
what?
the question that motivated this was, okay, suppose you don't know the place fields.
Mm,
Okay, this was a question that sort of that I had in a summer school. Actually, I was in one of these MBL marine biology lab
yeah. I was
summer
also
schools
there in
back in like 2006, right? So
I
this
was
paper
in
came out.
'95, so I'm even
Okay. I was in, I was a fresh postdoc. I was like,
yeah,
I'd maybe done a year of postdoc at that
yeah,
point.
mm,
And so I went to this MBL summer school, and there was a talk about place cells and and then of course I was in Ken Harris's lab when we were next to Bujaki lab, so I had learned a lot about place cells and place fields.
mm,
Um, but the idea was, okay, if you know the place fields and then you get the population vector, you can do some kind of Bayesian scheme and decode, right? And say this is the most likely position of the animal. And
mm,
so you're allowed you can decode the position in space based on the current population vector.
mm,
But that, of course, is if you know the place fields,
mm,
right? And so then the question um, that I had is, uh, what happens if all you have are the population vectors, right? And you don't know the place fields. So somehow, like, the place field is this artificial construct, right? It's the
mm,
experimenter correlating place cell firing with position in space,
mm,
and then constructing this map, this dictionary
mm,
between the outside world and the spike trains. And
mm,
so so I asked, well, and then later we asked, because I sort of shared these ideas with Vladimir Itzkov at the time, who was also a
mm.
postdoc, and so we started thinking about this together. What if you only had the spiking?
Exactly. So the experimentalists didn't tell you about the place cells, only gave you the population
They just
vectors.
gave you the spiking, right?
Okay. Mm,
Or and so it's like you could think of it as a sort of a challenge, like a data challenge. You could
yeah,
also think about it from the perspective of, like, you're a homunculus inside the
mm,
brain,
mm,
right? And you're just seeing the spike trains. Nobody's measured the place fields for you. And in the case of place fields, this is a particularly kind of, I think, relevant question because you get new place fields when you go into a new environment. And, the animal maybe doesn't, I don't know, there's no sense in which, like, where is the place field in the brain, right? It's not really clear if that's encoded anywhere or anywhere that's accessible. And so, so this is the question. You just have the spike trains. What can you say about the environment? Can you say anything? Right? That's the first question. It's like, can you say anything?
That's interesting question.
Right? And so it's really a question about the neural code and whether the structure of the neural code is reflecting the structure of the stimuli, of the space stimuli, right? And so, so what is the sort of obvious answer is you can tell maybe when place fields intersect.
So meaning that two place cells are active at the same time.
Right. If two place cells are active at the same time, their place fields probably intersect.
Yeah.
And if three place cells are active at the same time, there's probably a triple intersection. Right? So you can tell things like that. You can tell when place fields intersect. Okay, but what does that tell me? Right? And so here is kind of the beautiful thing. And this is, literally from kind of this first year graduate algebraic topology course, is there is this theorem called the nerve theorem. It's actually called the nerve theorem.
I sort of tried to read up and I got really confused about the name, but that's something.
Yeah, the name
means something completely different.
It means something completely different. Yeah. But it's called the nerve theorem because there's a combinatorial structure you associate to the scheme of open sets, and that structure is called the nerve, kind of like a skeleton. It's like a skeleton of an I don't know. It's like this name was given like 100 years ago and not nothing to do with neuroscience. But the idea is if you have a system of open sets, so now we're in topology land. Okay, and topology is really the study of how open sets interact. In fact,
so what's an open set again?
Yeah, so an open set, very abstractly, right? You define your open sets to be whatever you want them to be, but they have to satisfy certain axioms to make a topological space. But if you go back to familiar examples, like on the real line in the standard topology, an open set would be like an open interval. Okay. So open sets have a property where if you take a point in there, you have neighborhoods that stay inside the set. So once you include the boundary, like if I take the open interval 0, 1, that's an open set. If I close it, now it's no longer an open set. And part of how you can detect this is you have these points like 0 and 1, where there's no neighborhood of the point that stays inside the set. Always going inside and outside. So there's this.
That's an open set.
Yeah. But in an abstract topological space, open sets are whatever you want them to be. Actually, you just have to define this collection, and then they have to be closed under certain operations. So if you take unions of open sets, you should get an open set. Finite unions, if you take finite intersections of open sets, you should get open sets, and so on. So there are certain axioms that the empty set is an open set. The entire space is an open set.
Okay.
Good. So these are kind of the rules of a topological space. And with these rules, if you have a collection of open sets that cover some space, so this is kind of like place fields covering an environment, right? So covering means every point in the space sits inside at least one of those sets, one or more. Okay. Then you can construct what's called the nerve of this cover. And the nerve is obtained simply by checking what intersections you have. So first you start with kind of a graph. So you have a vertex for every set. So if I have 100 open sets, I have 100 vertices. And then I check if two open sets intersect, if I and j intersect, then I put an edge between I and j.
Edge is a line right between two nodes.
Yeah, abstractly, it's really just like the pair, right? But yes,
but I'm just because I just want to see this graph.
In a graph, a graph theory graph, not the graph of a function, but so you have vertices and edges. So you put an edge every time you have a pair that intersects. But then when you have a triple that intersects, so first of all, notice that if the triple intersects, all the pairs have to intersect.
Yeah.
right? If there's a
Okay.
triple intersection between I, J, and K,
Mm.
then I and
Yes.
J and K, and I and K all intersect as well.
Mm.
And so you'll have like a triangle, right?
Mm.
And if you also have the triple intersection, you fill it in,
Okay.
okay, and
Yeah.
so on. So you can build what's called it's a generalization of a graph. It's called a simplicial complex,
Okay.
and the simplicial complex is really just a collection of um, edges and higher dimensional simplices, and it's kind of a generalization of a graph, because in a graph you only look at pairs,
Mm.
you only record kind of interactions between pairs, but here you can do triples, quadruples, and so on. So if
Okay.
I have
Mm.
like if I have 5 place fields that intersect
Mm.
all in one point, then I will have like um, a 4-dimensional simplex
Mm.
sitting inside a region, created
Yeah.
by the 5 vertices.
Okay. Cool.
Okay. All right. So this is the simplicial column, and this is what's called the nerve of the cover.
Okay.
Okay. So you have your cover of open sets. You keep track of all the intersection data,
Also, and the cover is what was the cover again?
the original open sets,
Okay.
a
Exactly.
collection of open sets.
Mm.
So like the place fields.
Mm. Okay.
So the place
Cool.
fields would be an example of a cover
Mm.
of a space. And then you can construct this nerve. Okay. So this nerve in principle can be very high dimensional, right? So the dimension is actually controlled by the degree of intersection that you see.
Okay.
So if you have 10 place fields intersect
Mm.
at a point, then you'll have a 9-dimensional nerve, at
Okay.
least 9-dimensional. Okay.
Mm-hmm.
So it's some object. Okay. But it's an object that itself um, has topology. And so you can compute topological invariance,
Mm-hmm.
homology groups, and so on of this simplicial complex. And the magic is that the simplicial complex as a topological space
Mm.
is what's called homotopy equivalent or topologically equivalent to the covered space.
Okay. I see. I see. Okay. So this means that you can, if there's like a hole in this cover of place cells, there's also going to
Mhm.
be a hole in the
There's also
whatever.
going to be a hole in the simplicial complex,
Ah. Hmm.
right?
Cool.
And of course, I don't really want to build a simplicial complex
Yeah.
if I know my space, right?
No.
But the cool thing about applying this theorem in the context of the place cells
Yeah.
is that this nerve you can construct just from coincident spiking activity.
Yeah. Hmm.
So if you
I
see
see.
which collections of neurons spike at the same time, it tells you the nerve. It tells you what intersections you have,
Yeah.
even if you don't know the place fields.
Yeah. Exactly. So you can learn about the topology of the area that say the rat is moving around in, just
Right.
by even without having been told anything
Even
about
without
place
knowing
cells.
any of the place fields.
Yeah.
Of course,
That's
you have
cool.
to make, I should qualify all of this.
Yeah.
You have to make an assumption about the place fields,
Yeah.
right? So you have to make an assumption that they form what's called a good cover.
Yeah.
Okay. And a good cover is actually a technical term. And this will
Meaning
be
that
satisfied if you,
they have to overlap sufficiently or something.
well, no, I mean, it's actually about the topology of the overlaps themselves.
Okay.
So the overlaps themselves and the place fields themselves have to be contractible.
Hmm. I see. Contractible,
Okay,
and
so
that's
so this is a topological feature, but it's something that will be satisfied if your place fields are all convex.
okay.
So if they're all
Hmm.
convex sets, like the
Yeah.
traditional,
Hmm.
ellipsoidal
Yeah. I see.
view of a place field, then this is satisfied. If you have multi-peak place fields, it's not satisfied.
I see. Hmm.
Right.
Yeah.
And so actually in that 2008 paper, we actually tried to deal with the multi-peak place fields. We have some like supplementary figures dealing with that case.
Okay. Yeah.
But in the
Cool.
easy case, the theorem basically tells you immediately, even if you don't know the place fields, the neural code, right, that's given just by the spiking activity, the neural code tells you the intersection information,
Yeah.
how the
Yeah.
place fields intersect. And the intersection information is enough to recover topological features of the underlying space. And
Yeah.
that's what
Well,
the
yeah.
nerve theorem tells you.
Yeah. Oh, that was cool. That's quite elegant.
Yeah. So it's cute, it's
Yeah.
kind of like a um
Hmm.
yeah, it's cute, and it's not a very deep observation if you
Mm.
know about the Nerf theorem and you know about place fields,
Mm.
right? The
Huh.
very few people at the time knew about both,
Yeah.
and
But I guess
so
that's but I
yeah,
guess that's one of the things when you come from from a quite different field. Of course, it's
yeah,
a big sort of like the lots of you're quite confused. At least I was when I entered, and all this
yeah,
information that you have to deal with. Then, and sometimes you can bring in sort of like these things that which are maybe sort of quite well
hmm,
commonly used, and in some sense almost well, well not trivial, but at least sort of like
yeah,
low
yeah,
hanging fruit with one
yeah,
set of methods can be
yeah.
used because people are not aware of it
Yeah.
in the field.
Yeah, it is. I mean, I feel like this is very low hanging fruit. So it's like anybody who kind of knew enough algebraic topology
Mm.
and knew about place fields,
Yeah,
right, would have this idea. And in
yeah.
fact, I should say, in addition to me and Vladimir, who wrote that paper, there was another guy, Yuri Deb again, who was working in Lauren Frank's lab at the time, who had a physics background, but kind of a very theoretical physics background with topology. And he had also had this idea. So I
Mm.
remember very distinctly um,
Mm.
Vladimir at some point gave a talk about it at
Mm.
Cosine. So we had gotten,
Mm.
one of those like sort of selected talks at the Cosine conference back in
Mm.
2007 or something.
Mm.
And after the talk, Yuri Devagan came very excitedly, but also a little bit,
Yeah,
upset. I think,
yeah,
he's like, wait a minute, I had that idea. I'm writing this up, so it
yeah,
was kind of a simultaneous
yeah,
thing, but it's because it's a very obvious idea.
yeah.
It's a
But it's
very
like,
obvious idea for anybody who knew enough about both
mm.
fields,
Mm.
right?
Yeah,
Yeah.
cool. So that was the first, like, if one first application, and then then this thing about sort of like then when you looked into this correlation matrices to look about the like the structure
Mhm.
of these. So now, yeah. So what is that all about? Like the yeah. So that was they had this 2015 paper
Yeah.
in
In PNA.
PNAS, right? Mm.
Yeah. Yeah. So the 2008 paper we had simulated place cells, right?
Mm-hmm.
So this was still kind of early days. Um, I mean, now I feel silly because the recordings are so much more impressive, but at the
Mm.
time it was kind of difficult to get data where you cover the entire space, where you have enough place cells and place fields to cover a whole space.
Mm.
And so, we tried doing this, but we were working with Eva Pastalkova, who had been a postdoc in Yuri Bujaki's lab, and then transitioned to one of these sort of junior fellow kind of positions at Janelia. Um, and so she had collected a lot of place cell data, hippocampal place cell data. And so we decided, okay, let's try to use topological methods on this. And the thing that ended up working the best was to look at the pairwise correlations as a proxy for this overlap information.
Mm.
So the idea being the data was a little too noisy to just sort of take the naive thing we wanted to do, which then later was actually done with the grid cells, but we couldn't
Mm.
really do it at the time with the place cell data we had, was to take the time windows, right?
Mm.
And look for coincidence spiking and build the nerve and all of that. So we wanted to kind of follow the same strategy that we had done in our computational paper in 2008.
Mm.
Um, but the data was too noisy. And so
Mm.
then what we ended up doing was looking at which I think was actually a nice idea in and of itself, um, maybe more broadly applicable in the long run, is to look at pairwise correlations,
Mm.
right? So here we had, say 80 or 100 place cells,
Mm.
and we computed pairwise correlations between them to get a
Mm.
pairwise correlation matrix.
But I mean, so pairwise correlations, like coincident firing, is like pairwise correlations, isn't it?
Yeah, coincident firing is like pairwise correlations, except we wanted the fine in the original 2008 paper. We needed the finer information about the higher order,
Okay, I
right? So
see.
it's like we needed to know not just
Ah,
pairwise coincidence. Remember, to
I
build a
see.
sequential complex, it's not just the edges of the
Yeah,
graph,
of
but
course.
also
Yeah, if you have more than
and
two,
that was
then
right, and
yeah.
that was a lot harder to get like good sampling
Exactly.
in. Right?
Cool. Yeah.
So we decided, okay, we'll stick to pairwise correlations, which
Mm-hmm.
is like coincident firing, but looking over the entire recording.
Mm-hmm.
And sort of the amazing thing about the pairwise correlations is that matrix, right? If you look at you have sort of n by n matrix where the
Mm-hmm.
ij entry is the correlation between the ith neuron and the jth neuron
Mm-hmm.
across a recording. that matrix has a lot of structure in it if your neurons have place fields.
Okay.
Okay.
Yeah.
If your neurons are sort of dictated by some underlying geometric coding, that matrix will have a lot of structure in it that's very different than if you just scrambled
Yeah.
the ordering of the
Exactly. Because
correlations.
two neurons, which just happens to cover the same position in space, will have like a strong correlations.
Right. And the other thing that happens is if neurons I and J are strongly
Mm.
correlated and J and K are strongly correlated, there's a
Mm.
good chance I and K are strongly correlated.
Yeah.
Whereas if you looked
Mm.
at something like if you looked at a random correlation matrix,
Mm.
there would be no expectation that just because, I and J and K
Yeah.
correlate, that I and K will also correlate strongly.
Mm.
Okay.
Mm.
And that property, that sort of, if there's a strong correlation with a common neuron, I with J and J with K, that then I and K will be strongly correlated. That is actually sort of the correlation version of the triangle inequality when you
Mm.
turn things around and think about distances.
Yeah. Okay. Yeah.
Okay.
Mm.
All right. So the triangle inequality, back
Mm.
to, this is back to geometry, right? This is back
Yeah.
to distances, which I've been telling you that we throw away, but we don't completely throw them away, because actually
Mm.
some of what we can detect topologically is the
So
presence.
the triangle is that like the distances from A to B plus B to C is smaller than A to C or something, smaller or equal to.
Larger. Yeah.
Larger, exactly. Larger, exactly. Yeah.
Right,
Mm.
right, right. Distance
Yeah.
from A to B plus
Mm.
distance from B to C has to be smaller than going directly from A to C. Has to be
Larger.
larger. Sorry, than going I said it the way you
Okay. Okay.
has to be larger than going directly
Yeah.
from A to C,
Yeah.
right? So that triangle inequality is one of the fundamental features of having a metric.
Mm. I
Okay,
see. Yeah.
and so it's actually in the definition of a metric that you have to
Mm.
satisfy this
Yeah.
triangle inequality.
Ah.
And
And
if
when
you
you have a
turn it,
metric, you start talking about geometric structures. Is that
yeah, right.
exactly? So
And
that's sort of
so
the link. Mm.
right, and so if you have um, if your correlations are really dictated by geometry in some sense. So what would that mean? That would
Mm.
mean that I can think of my neurons, right, as representing positions in some kind of space.
Mm.
It might be physical space, like for place cells. It might be, like a visual feature space, an
Mm.
olfactory space, right? If I can think of my neurons as representing stimuli that live in a geometric space,
Mm.
right? And then the correlation between two neurons, would
Mm.
drop off with distance.
Yeah.
So the closer, if two neurons are representing features or positions in the space that are nearby, then they should be highly correlated.
Mm.
And if they're representing very different features in the space, they should be less correlated.
Mm.
Okay. So if you imagine correlations drop off with distance, right?
Mm.
Then the triangle inequality, turning it around, right, is
Mm.
telling you that if A and B are strongly correlated and B and C are strongly correlated, then A and C should be very strongly correlated too.
Mm. Yeah. Mm. Yeah.
Okay. And
Mm.
so this property is is something that you would see in your correlation matrix
Mm.
potentially, right?
Mm.
Except that it's not quite, they're not really distances. So you can't just check like, is this a distance matrix? Because they're
Mm.
not. The correlations are some nonlinear transformation on
Mm.
the distances.
Yeah.
Okay.
Mm.
And so what we found with the persistent homology tools,
Mm.
right, the topological data analysis tools, is that you can apply them to a correlation matrix
Mm.
and they will pick up on these properties, right,
Mm.
independent of the nonlinearity that you use to transform from distances to correlations.
Because there, I mean, so because this could be in practice, these data could be spikes of firing rates, but they could
Mm-hmm.
also be some like calcium imaging.
Calcium imaging,
Yeah,
exactly,
yeah.
which is what
So there's
I'm
some
working.
kind of, so there's some, yeah. So, but it's
There's
not
some kind
like
of
a,
nonlinear transformation,
yeah,
right? And so you're like, okay, there's some kind of so maybe there are true distances somewhere,
yeah,
right? The neurons do reflect positions in a geometric space, some kind of
mm,
geometric space,
yeah,
but there's some kind of nonlinear transformation that's taking me from those distances to
mm,
my correlations,
yeah,
right?
mm,
And all I need, and so what the topological tools will do for you is they will find invariants of your correlation matrix
mm,
that throw away that nonlinear transformation.
mm,
So what you do need to know, the assumption you do need to make is that shorter distance is stronger correlation.
Yeah.
But other
So
than
there's a
that,
kind of
right, so
like
that there's like a monotonicity to the
yeah,
transformation.
because I think what you when I read your paper, so that for example the eigenvalue spectrum is not conserved at all.
Not at all.
No,
Right.
but this kind of some kind of this ordering of the
Mhm.
and ordering of the size of these matrix elements is because of this monotonicity,
Right.
and then you can use these some tools which somehow from topology,
Yeah.
and these tools, and that's like all this. Now we're coming into these things which was I just learned about all these Betty curves and stuff.
Yes.
Yeah,
Yes.
tell us about the Betty curves
Yeah.
and like
So
these tools.
this is where the Betty curves come in, right? So the
Mm,
idea is um, the structure you want to kind of take from that. So we want to throw some information away, right?
mm,
We don't know what this nonlinearity was, and we don't care,
no,
right? We want to see, is there an underlying geometric structure? Is
mm,
there a triangle
yeah,
inequality in
exactly.
some sense morally, right?
Because even if we didn't care, even if we did care, we couldn't say well,
Even if we
we
could,
wouldn't
even if
know. We wouldn't know,
we
right?
don't know what it is,
No,
right? And so we
exactly.
want
So
to,
then,
right?
yeah,
So in the same way, I mean,
yeah,
the analogy I like to make is when you look at things like eigenvalues,
mm,
right? They're invariants too, but they're invariants under change of basis.
mm,
Because
yeah,
there, sort of, this is a classic physics setup. The
yeah,
arbitrariness is what you chose to be your x-axis, what you
yeah.
chose to be your
So you
y-axis,
can
right?
sort of,
It's the
yeah,
coordinate system is what's
yeah,
arbitrary, and
mm,
you always looking for invariance under change of coordinates, right? In
yeah,
fact, Einstein did all of general relativity. It's
yeah,
basically it's
yeah,
based on this concept that you want physics to be invariant under change of coordinates,
mm,
right? And so
yeah,
most of linear algebra is set up with that idea in mind. All the invariants are invariants under change of coordinates.
yeah,
Okay.
exactly.
Right?
Yeah,
Whereas here, change of coordinates is actually a serious
yeah,
change because you're changing your neurons. Like what, I don't even know what that means, right? So
no,
we don't want necessarily invariance under change of coordinates. What we
no,
want are invariants under this nonlinearity, right? That may
mm,
be applying entry wise and maybe
mm,
affecting the sizes of things, but not necessarily the ordering of
mm,
those entries. And so that's
yeah,
kind of the
mm,
motivation, right? It's like we
mm,
want different kind, and I actually do think that there is potentially a field of matrix theory, right, that should develop that really looks for this kind of invariance
okay,
as
yeah,
opposed to the traditional linear algebra ones. But
I
anyway, that's
see.
a
Mm,
separate discussion. Um, but okay, so what is the idea behind the Betty curves? So the idea is to use tools from persistent homology, which
mm,
were originally designed uh, with the assumption that there is distance, right?
mm,
That you have sort of um, data points in some Euclidean space, and there really are distances. But the observation is that the topological pipeline
mm,
that persistent homology implements
mm,
actually doesn't care about those values. It really only cares about the ordering, because this
okay.
is what you do when you compute persistent homology. It's actually
Mm.
very similar to the nerve construction I told you about before.
Okay. So just no, just want to the persistent homology is the name of this quite
Yeah,
commonly used now this tool for
right.
data analysis. And well, persistent means or persistent, I guess, but homology. What is meant by
Yeah, so
homology here?
homology is it's what we were computing before from the nerve, but
Mm,
it's topological invariance,
okay.
and so the easy but not quite correct way to think about it is it's counting holes.
Okay.
So for instance, the coffee cup and the donut, right?
Okay.
They
Yeah.
have a hole, and it's like a
Yeah.
one-dimensional hole because you can bound
Yeah.
it
So
by a
they are
one-dimensional.
homologous. Mm.
What?
So they are homologous.
So they
Yeah.
have what's called non-trivial homology.
Okay.
Whereas
Mm.
a ball, a
Mm.
filled-in ball,
Yeah.
has no non-trivial homology. You can sort of
Yeah.
contract it to a point. But a hollow ball,
Mm.
okay, so like the surface um,
Mm.
like a sphere, right, with nothing inside,
Mm.
that's a hole as well. That's a
Mm.
higher dimensional hole. So
Yeah.
that would be tracked by a different homology group.
I
So the
see.
homology groups are groups or vector spaces that whose dimension the dimension of these vector spaces are sort of counting the numbers of holes, except it's
Okay.
a little more subtle because sometimes there are two holes that are morally equivalent, and they
Okay.
get identified. So there's a quotient construction happening there. It's a
Did you say
little tricky.
morally equivalent? No.
Well, yeah, I
Uh,
mean they get identified under the
okay.
quotient construction.
Okay. Good.
Okay, so
Mm.
if I have a cylinder, right?
Hmm.
They say, oh, there's a hole on this side and a hole on this side, but they're really the same hole.
Okay. Okay. I see. Mm.
Okay,
Yeah.
so the homology would not double count that. It would be
Mm.
careful not to double count that.
I see. Mm.
Hmm.
And then, so okay, so you have these different these homologies groups, and then, and now you're almost at the Betty curves. Or
Yeah. So for a given simplicial complex,
mm,
right, you can compute these homology groups. So for instance, back in that 2008 paper, right, we looked at all the intersections. We made a single simplicial complex with all
mm,
the intersection data of the place fields, and then computed the homology groups, and the dimensions of them are what are called the Betty numbers. Okay,
okay,
so these are the things that actually count the number of holes
okay,
in each dimension.
yeah,
Okay,
okay,
the Betty zero is an interesting one. So there's a zeroth order one called Betty zero, and that actually counts the number of connected components.
okay,
Okay, so if you have disconnected regions in your topological space that are
mm,
not,
I
that
see.
are isolated from each other, they would contribute to Betty zero.
Okay,
Okay,
mm,
so if you put the coffee cup and the donut together and consider that union as a single topological space, it would have Betty zero equals to 2 because there
okay,
are two
I
connected
see.
components.
I
Okay,
see. Yeah. So that's Betty zero.
yeah, Betty one is what counts that hole
Okay.
that you see in the coffee cup.
Yeah.
Okay, Betty two is the hole from the sphere.
Okay.
Okay, and
Yeah.
then there are higher dimensional holes. So
Mm,
these holes are bounded, like the one dimensional ones are bounded by a circle,
mm,
one dimensional circle. The two dimensional ones are bounded by a two
yeah.
dimensional sphere, like the surface of a ball,
Mm,
and so on. So that would be so Betty zero, and Betty zero is connected components.
mm.
So Betty zero, Betty one, Betty two. I think we went up to Betty three in that paper. And so these are counting holes of different dimensions.
In which are something, so how are they, how do these, okay, starting with these correlation matrices.
Yeah. So starting with the correlation matrices, um, so you can, if you impose like a single threshold,
Mm,
okay, so say I want to consider all the correlations that are higher than some fixed amount. Okay,
mm,
so I'm going to say these neurons are highly correlated, the other ones are not. Okay, so if I put a single threshold, I'm going to get a graph.
mm,
Okay, so the graph is going to, so I'm going to have a node for every neuron,
mm,
and then I'm going to have an edge between neurons I and neurons J, right? If the correlation between I and J is above the threshold,
I see. Yeah.
right? And if it's below the threshold, there's no edge, right?
Mm,
This graph will summarize, right, who's above and who's below my threshold.
mm,
Okay, and
mm,
then this is sort of the thing that's coarser than the nerve that I told you
mm,
before. Then what you can do is if you have, say, three neurons, I and J are connected, J and K are connected, and I and K are connected, you go ahead and fill in.
okay.
So when
Yeah.
you have all the lower order connections, you go ahead and fill in the higher order simplices.
Okay.
Okay. And so then from taking the pairwise correlation matrix and just putting a simple threshold, I
Mm,
get a simplicial complex. First, I make my graph, and then I go ahead and fill in every time I have a click, every time I have all to all connected, if I have four neurons that are all to all connected, I go ahead and put in a tetrahedron.
mm,
So I make my simplicial complex. It's a little bit of a cheaper way because I'm not actually checking that there's a four-way intersection. I'm
okay.
just assuming there is because I have all the pairwise ones.
Okay. Mm,
Okay.
yeah.
So then from that single threshold, I get a simplicial complex. I can compute the homology of that simplicial complex, and I get homology groups and then Betty numbers.
Okay.
So
Yeah.
from one threshold, I get a Betty zero equals,
Mm,
say, 5. Betty one
mm,
equals 3. Betty two
mm,
equals 0, and so on.
yeah.
Okay.
Mm,
For a single threshold. All right.
mm,
And so that's playing a game very similar to what we did in the 2008 paper.
mm,
Now, where does the persistent come in? The persistent homology comes in because you want to consider all the thresholds,
yeah.
right?
Mm,
So it's
mm,
like that choice of threshold is arbitrary.
mm,
Okay. And
yeah.
so the idea is what if I slide the threshold? Okay. So as I slide the threshold, When the threshold is very, very high, say no correlation is above it. So I get an empty graph. I just have my nodes, no one's above the threshold, no pair. Then I start sliding it down, right? And now I start to get, my first pair is above threshold, right? Say neurons 1 and neuron 5 are above threshold, their correlation is above threshold. So now I connect. So that's my first graph. And I compute the homology of that. It's very stupid homology. It's a lot of connected components because I have a very disconnected graph, right? But I don't get any higher order holes. Then I start sliding. And at every stage, I'm adding a new edge to the graph. And if you think about it, what matters is not the values of the correlations in terms of what sequence of graphs will I get. What matters is the ordering of them, right? The highest correlation will give me the first edge. The next highest correlation will give me the second edge, and so on, right? And the order in which I add edges will determine what holes I get. So there are ways that you can add edges. And so at the beginning, I start always with the empty graph, just vertices and no edges. At the end, when my threshold comes all the way down to 0, I end up with the complete graph, right? Everything is filled in, right? And that's also topologically trivial, okay? And in between, right, as I journey from the empty graph to the complete graph, I can take many different paths. I can add edges in a way that I never get holes, higher dimensional holes, or I can add edges in a way that I get lots of holes. And in fact, if you take a random matrix, a random symmetric matrix, and you think of it as a correlation matrix, and you add, edges, that's like adding edges randomly, like building an Erdős-Rényi random graph by adding one edge at a time. Okay. So if I add edges totally randomly, I actually end up getting tons of holes in between. There are in between stages. Say I have 100 vertices. There are in between stages where I just get explosions, lots and lots of holes. Betty 1 goes really high, Betty 2 goes really high. And so on.
Yeah.
But there are other ways. If I start with like a rank 1 matrix, a rank 1 symmetric matrix, I'm always going to add edges in a way that produces like no holes.
I see. Yeah.
Right. And so the degree to which you're producing holes is reflecting structure in the matrix.
Yeah. Exactly. Yeah. So each matrix, or at least like typically different matrices, will have different Betty curves, right?
Right. And so the Betty, and so I didn't say what the Betty curve was. Sorry.
Okay.
But
I'll tell what a Betty curve is.
Yeah. So we have this sliding threshold. At every threshold, I get a simplicial complex, right? I make the graph and then I fill in the clicks. So I get what's called the click complex, and I compute the Betty numbers for that. And then the Betty curve is tracking the Betty numbers as I go through the sequence of graphs, which is called a filtration. It's called a filtration because they're nested. So each graph goes to the next one by adding an edge. So the set of edges are always contained inside the next one. So it's like a nested sequence of graphs. It gives me what's called a filtration of simplicial complexes, and then I compute Betty numbers at each stage in the filtration, and that gives me a curve. So the curve is like I have a parameter T or rho, which is the edge density, tracking how many edges I've added. And then I get the Betty values at every stage. So that's the curve. And persistent homology is what's used to get that sequence from a single matrix.
Exactly. So then for example, you can get this almost like this lookup table of different Betty curves corresponding to different types of matrices. Is that it?
Right.
So you have like these different signatures. If completely random, you get one set of Betty curves. And then if you do this on, say, experimental data, you can see to what extent it is sort of random or not. And that's the idea, right?
So the easiest thing to do is check, like, does it look like a random matrix? And typically it doesn't, right? It's very far from that. So one of the reasons this is actually like a useful method is that it is very consistent for random matrices. So I like to make the analogy with eigenvalues and the Wigner semicircle law.
Mm.
So if you take a random
So the
symmetric
Wigner semicircle law is that some kind of distribution of eigenvalues,
of
right?
eigenvalues for large random symmetric matrices, right?
They
And it's
follow some kind
very
of.
stereotyped, right? So you go into MATLAB, you make a random symmetric matrix, right? You compute the
Yeah,
eigenvalues, and it just follows this
exactly.
distribution,
Yeah.
right? It's crazy. They're like very, very regular, right?
Yeah.
Random matrices are all the same. You know?
I see.
But in this exactly the same way, the Betty curves of random matrices are also all the same.
I
This is
see.
not eigenvalues at all, right? We're doing something
Okay.
completely different, but these
Hmm.
curves are extremely stereotyped. And so
Yeah.
the error bounds on them if you make like, thousands
Mm.
of random matrices and
Yeah.
compute, Betty 1 curve,
That's true. So
the error
whenever you
bar
have a
is
random
really
matrix,
tight.
you can use this Betty curve filter and check.
Right. You can
Yeah.
really check like
Yeah.
this looks random or
Yeah.
not.
Mm.
Right. And so we're replacing with, again, the project is to kind of replace the traditional eigenvalue based analysis
Mm.
with a different kind of analysis, which is now going to be invariant
Mm.
under these monotone transformations
Yeah.
instead of changing
Mm.
coordinates. And so
Mm.
yeah, so it's very stereotyped for random matrices. It's also very stereotyped for what we call geometric matrices.
Mm. I
Okay,
see.
so if your correlations, as in the case of place fields and place cells, in the case of place cells, right, we believe the correlations are coming from nearby positions in
Okay.
space, right? So if
Yeah.
two place cells are encoding nearby positions and they overlap a lot, they'll be highly correlated, right? And if they encode faraway positions, the correlation will drop off, right?
Okay.
Okay.
Uh,
And so if you take a correlation matrix that's coming from place cells, then you have this phenomena with the triangle inequalities.
okay.
But
Yeah.
in thought of in the correlation space. So it's like it's
Mm.
the geometry, but the geometry is forcing a structure to the ordering of the matrix entries.
Mm. But how does, I mean, if you have like different sort of place cell arrangements, some with very lots of overlap and some with little overlap, will they get very different Betty curves or
Not that different.
no?
No,
Okay, so
not
you
that
cannot
different.
really learn too much about the. You learn about the geometry, that there is some
You
geometry
learn about
behind
what
there.
they're covering exactly,
Yeah.
and that's
Yeah.
the idea. It's like somehow the place cells are a window into
Yeah.
the underlying space.
I see.
And so you learn something about the space. And so what we expected was that if we did the same process and computed Betty curves for place cells, that
Mm.
we would get something very non-random, but also something that would look like Betty curves produced by distance matrices,
Okay.
right? So if you take just like a distance matrix, right,
Mm.
and then and maybe take the minus of it or one minus it so
Mm.
that you have
In
higher
some kind
distance,
of two-dimensional space, then
two-dimensional or low dimensional
low dimension.
space,
Okay.
in some kind of low dimensional space, then we expect, okay, there's going to be all this extra structure. And what that effect has, the effect of all that, the effect of the geometry is basically to close up holes quickly.
Huh.
So in the
Mm.
case of the random matrix, you start getting these really these high dimensional holes. They last for a long time because they only close up when you get extra edges connecting things, and then you fill more in. You have to
Mm.
fill in the hole to get rid of it. And what happens in when you have an underlying geometry is that the way the correlations are organized, you fill up those holes really quickly, and so you get much smaller Betty curves. And in the extreme case where it's like
Mm.
a rank one matrix, highly
Mm.
structured, you just never get higher dimensional holes.
Mm. Mm. So I think you showed in 2015 you used this on sort of like place cell data and
Mm-hmm.
illustrated this point about the geometry. And then there was a later paper about olfactory space, I think from the Sharpie lab or something, where
Yes,
they said something about the hyperbolic geometry. What so what does so that's
right.
interesting because obviously olfactory space is different from real space.
Right, exactly. So in
Yeah.
the in the 2015 paper, which by the way was done with Eva Pastelkova's data, Vladimir
Mm.
Itzkov was on that paper as well. He was on the 2008, and then Chad Giusti was a very talented postdoc who did
Mm.
a lot of this work. So we were we were applying the method to a space where we kind of knew what the answer should be,
Mm.
right? It's like,
Mm.
of course, place cells are dictated by geometry, by Euclidean geometry, right? Like of
Mm.
two-dimensional space or something very simple like this. And so we expected, place cells. We expected Betty curves to reflect that geometry, and it was a Euclidean geometry that we were testing against.
Yeah.
And so and we did see that, right? So, but it was like a proof of principle, because it wasn't, I mean, in some sense, we didn't learn anything new about place cells. We learned that the method was capable of detecting what we expected.
Mm-hmm.
Okay. Without knowing. And well, I mean, the key innovation, right, is again, without knowing the place fields. So we're
Mm-hmm.
only by knowing the correlations, which is something that you can get just from the spikes. Without knowing the place fields, we could see this geometric structure. Now, then Tanya Sharpie did this lovely study in 2018 in her lab. And so they went to a space where, we know a lot less about how it's
Yeah.
organized, olfactory
Yeah.
space, right? So
Exactly.
olfactory space is one of the
So
most mysterious ones.
how are smells organized, right?
Right.
That's
How are smells organized, right?
yeah.
What's the dimension of it? Is it
Yeah.
Euclidean? Is it hyperbolic?
Yeah.
Like what is it, right?
Yeah.
And so she was able to use the same, and again, you have these like hidden nonlinearities, right? You don't know what's the transformation between distance and whatever the space is, and distances in the space, what's the transformation between those distances and the correlations, right? So again, you have this like monotonic nonlinearity that you don't understand. And so you want a technique that's invariant under that kind of uh, under those kinds of changes. And so she was able to use exactly the same method, the Betty curves, but this time she did not get consistency with Euclidean space.
Mm.
Right. What she saw was that the olfactory data was consistent with hyperbolic space.
Yeah, so what would that mean? That means that there are things are yeah. What would hyperbolic space mean in this context?
That's a good question. Um, no, I mean, I think so. Yeah. So with Euclidean space, there are these triangle inequalities that I was telling you
Mm.
about, right?
Yeah.
You still have that with hyperbolic space, right? So it's still metric space,
Mm.
um, but somehow you have this. Uh, you have a structure that's almost like hierarchical in its organization. So the way the
Okay.
distances behave, you can think about. So hyperbolic space is often used to model networks, in fact, right, and model spaces where the points are kind of hierarchically organized.
Okay.
And so that I think is perhaps the key insight. I mean, and
Mm.
that's what I think Tanya would tell you as well,
Mm.
um,
So
because
how did she find this? She made some hyperbolic matrices, and
right.
so that the Betty curves looks a little bit like what we see in experiments. Is something like that?
Right. So the lovely thing about this technique, of course, is because it's invariant to these transformations.
Mm.
If you compute the Betty curves for the actual geometric distances,
Mm.
right, they should be the same,
Yeah.
right? You can take the original distances or the transform thing, and it'll give you the same answer,
Yeah.
right? And so you can make sort of control data sets, right? Like by actually taking distances, and that's what we did
Okay.
for the Euclidean space Betty curves, and that's what she did for the hyperbolic space Betty
Okay.
curves. She sampled randomly points from different hyperbolic spaces of different
Mm.
dimensions and different sizes,
Yeah.
and found that and then
So
computed the Betty curves in all of these cases, and found that the data was consistent with hyperbolic spaces
I
more
see.
than
So you should
Euclidean.
make this like database over Betty curve showing that this
I
space
know, no,
like a lookup table for
this is for real, an idea that's out there that some of us are working on.
really.
Is to try to make, yeah,
Yeah.
because it shouldn't be, yeah. It's that the tricky thing, and it's already tricky with hyperbolic spaces,
Yeah.
is sampling it well and
Yeah.
uniform. Like, what does uniform sampling mean in that case? With
Yeah.
Euclidean space, it's kind of easier, but
Yeah. Mm.
yeah, no, I mean that's sort of the idea. But yeah, so I mean the key is that they give you signatures, right,
Mm.
of different kinds of spaces, and so then you can use them to see. And
Mm.
again, without knowing the receptive fields, right?
Mm.
So again,
Yeah.
with the olfactory data, the key is you're looking at the structure of the code. It's the
Mm.
neural code itself, right,
Mm.
and
Mm.
um, not the dictionary.
Yeah. So okay, so now up to this, like what I call this more like if you start, I mean, this topological data analysis, or which is sort of then, I guess, I mean, you already talked about topological data analysis, but there are like this work where they use this persistent homology things and sort of add, what do they do? They add some kind of like some what's called something called the RIPS complex and
Yes.
stuff like that. So that, I guess, it was started with this one, a very early paper by from on head direction cells from Ila Fiete's lab. Didn't they use some kind of persistent homology?
They use more of the classic setup of persistent homology.
Okay,
Yes.
can you tell about
Yes.
that or?
So that is, yeah. So that's the original. Okay, so I should back up. So these tools started being developed about 20 years ago in the
Okay,
applied math community, right?
yeah.
So mathematicians, topologists by training who wanted to like do applied math. So some of the names are like Gunnar Carlson and Edelsbrunner and Rob Greist and many others, right?
Hmm.
Um, Nothing to do with neuroscience.
No.
I mean, some of them have dabbled in neuroscience at this
Sure.
point, but like
Sure.
originally, the idea was to look at point cloud data. Okay,
Hmm.
so it's kind of like it's the 21st century. Data is coming. Data is everywhere, right? And um, in many fields, including in neuroscience, right, data often comes in the form of what's called point cloud data. So it's like we were saying, like the population vectors. You have n neurons, you have their firing rates at some point in time. That gives you a vector in n-dimensional space, where the ith coordinate is the firing rate of the ith neuron, right?
Hmm.
And so if you have many of these, you have a bunch of points, and it's like this is what they call a point cloud, right?
Hmm.
So the question is, does that point cloud, which is typically coming in a very high dimensional space, right?
Hmm.
Does it have any structure to it, right? Is there a shape? And of course, this is the same question you try to address when you do something like principal component analysis,
Yeah.
right? So PCA is asking the same question. It's like,
Yeah.
what is the structure of this point cloud,
Yeah. If there are
right?
some lower dimension, like you can reduce it to some
Right.
lower
Can I
dimensions.
reduce it? Is there some lower dimensional? Is it really kind of like an
Hmm.
ellipsoidal thing, but living in a lower dimensional slice of the space, right? Or is
Hmm.
it really like a high dimensional?
Yeah.
So, so tools like PCA and multidimensional scaling and all kinds of these kinds of things, isomap,
Hmm.
etc. They're all asking the same question: what is the shape of this point cloud data, right?
Hmm.
Can I think of it as living on a lower dimensional manifold, for example?
Yeah. So that's
Okay.
all this, like when people talk about neural manifolds, this is what they talk
Right.
about.
When people talk about neural manifolds, they're asking that question. If I look
Hmm.
at the, population vectors or response vectors,
Hmm.
the neural code, what
Yeah.
have you, right? Does
Yeah.
it live on a lower dimensional manifold? Because of course,
Hmm.
I'm embedding it in my 200 dimensional space because I happen to record 200 neurons,
Hmm.
right? But is it really 200 dimensional? Probably
Yeah.
not, right? It's like
Hmm.
somehow it's right. And so it's the same question, but the nuance, right, is to ask, is there topology to it?
Hmm.
Okay, so
Yeah.
if my point cloud data were living on the surface of a sphere,
Hmm.
maybe
Yeah.
a three-dimensional sphere, a four-dimensional sphere, two-dimensional sphere, even, right?
Hmm.
And I did these sort of projection techniques like PCA, I wouldn't see that.
Okay. Yeah.
Okay. I wouldn't
Hmm.
see that. I would like take these, projections and I would see like a point cloud all filled in,
Yeah.
right? But I wouldn't know that there's a hole in the middle,
Ah. Hmm. I see.
right? So a
Yeah.
lot of these techniques kind of fail to detect this kind of structure where
Uh-huh.
there's a hole in the middle, okay?
Hmm.
And so
Hmm.
this is where topology, so, going back to the very beginning of our conversation, right? Topology doesn't sound that powerful,
Hmm.
right? But it is. And it's not that you want to use it at the exclusion of other tools, right?
No.
It's
Hmm.
certainly missing things that other
Yeah.
tools are picking up,
Hmm.
but it does pick up things that other tools miss,
Hmm.
right? And
Yeah.
so this
Exactly.
is right. And so, like, if your data has some kind of structure, like a hole in it, right, then the topological methods can pick it up. And the
Hmm.
way that it works is you imagine, okay, say my data is sampled um, from a sphere, okay?
Hmm.
Say I can think of it as like really living on a sphere. Well, I'm not going to, if I just look at the points as a topological space, that
Hmm.
sphere structure isn't there. I just have a bunch of points. Okay. But if I put little balls around my points and start
Hmm.
growing those balls until they connect up, then at some point, my space with the little balls is covering a sphere. So I should see it,
Yeah.
right? Okay, and so this idea of like the growing balls is really the idea of putting a threshold on the distance matrix.
Mm. Yeah.
So if I compute the distance matrix, which is really easy to do, so I have my points x1 through xn, and I compute pairwise distances. So two of those balls will intersect when the radius of the ball, which I'm sort of growing,
Mm.
is over half the distance between the points.
Mm.
So
Yeah.
if I know the distance between 2 points, right, and if I know the ordering of those distances, I know in what order my balls are going to start intersecting,
Mm. Mm.
right? And so then the persistent homology idea is to take that distance matrix, take a sliding threshold,
Mm.
just like we were doing with the correlation
It's
matrix.
like increasing the radius of the balls, right?
It's like increasing the radius of the ball, right?
Mm.
Except now the threshold is going backwards, right? So it's
Mm.
like I want closer distances to connect up first, right? So I want everything that's below a certain distance,
Yeah.
right? As I increase the radius of my ball, I want to connect up points that are below a certain distance because
Mm.
that means their balls are intersecting,
Yeah.
right?
Mm.
And then I slide the threshold and I get the sequence of graphs and I get the sequence of simplicial complexes by filling in triangles and tetrahedra when I have all the edges. And that's the Rips complex.
Yeah.
So I've
Mm.
already described it to you.
Mm.
It's called the Rips complex or the Vietoris Rips complex when the matrix is a distance matrix.
Mm. Excellent. Yeah.
Right.
Mm. And then you do this. Well, if you think about the balls, then so if you sort of increase the size of the balls, then for a long time, for many radii, you will have this hollow ball.
I will have this big thing,
Hollow
right? So
ball.
I will get a simplicial I will get a Rips complex whose topology reflects again using the nerve theorem kind
Mm.
of idea, right? Whose
All comes back to the nerve theorem.
it all
That's what I
comes back
want
to
to.
the nerve except this is yeah, so I mean the Rips complex I should say is
Uh,
a little coarser than the nerve, right? Like
mm.
we're cheating. I mean, it's this idea
Yeah.
I was telling you before. It's like we're just filling in when we have all of the pairs.
Mm.
Right? If I have
Mm.
three pairs, IJ, JK, and IK, I fill in the triangle, whether or not they actually have a triple intersection.
Mm.
Okay.
Yeah.
And there are theorems, right? There are theorems that tell you this is okay, that
Mm.
you're gonna make mistakes, but the mistakes are gonna be short-lived.
Mm.
So it's like you may have three um, 3 points whose balls pairwise intersect and don't triple intersect, right?
Mm.
So
I see.
you may get a little hole there that's not
Yeah.
real,
Ah.
but as soon as you increase the radius a little more,
I see.
you're going to
Mm.
fill it in. Okay, and so there are theorems that tell you this is sort of okay, right?
Mm.
And you can use this cheap version, the Rips complex,
Mm.
um, which is exactly what we were doing with the correlation matrices of the
Mm.
click of just
Mm.
filling in clicks,
Yeah.
and then it's the exact same game, right? So
Mm.
you have your sequence, your filtration
Mm.
of um, of complexes. For each one, you compute homology groups.
Mm.
And then the power of persistent homology is that you can trace the homology cycle from
Mm.
one to the next. And so originally it was envisioned not for computing Betty curves. So
Okay.
Betty curves actually throw some of the information away. Originally it was envisioned because you want to see that cycle, that hole that we were
Mm.
just talking about from the sphere, and
Yeah.
it's going to live for a while, right?
Yeah.
But it's going to live for a while. As you're changing the radius, you're changing the simplicial complex. And so you have to have a way of tracing that homology cycle from one complex to the next, from one topological space to the next.
Mm.
And so there is kind of a subtle math question there, like how do you identify this is the same homology
Mm.
cycle? And so you want to, and
Mm.
then what you want is you get these things called barcodes, and you look for very long bars, and those are
Mm.
kind of the
Yeah.
topological features that you
Because
think
at
are.
some point, if even if this have all this living all these points on the sphere, if the
Mhm.
balls just get too big, the whole is going to be swallowed, right? And
Right.
vanish in the
So,
middle.
so in the same way that with the correlation matrices, right, you
Yeah.
always start with the empty graph, you always end up with the complete graph. It's
Mm.
exactly the same here. You always
Yeah.
end up with the complete
Mm.
graph. But the path that you take, right, as you're adding edges, that's what's totally different depending on
Mm.
whether or not you have these
Yeah.
holes.
And then you have this, of course, back to these head direction cells, because that
Mhm.
then I guess, yeah. So what was the story there? They use this
So
to
the
see
story there,
that.
right?
Yeah.
So the story there, this is the Ela Feet paper you're talking about, right, from 2019, I think.
Yeah.
Yeah. So the story there is the head direction cells are encoding an angle, right?
Yeah. Exactly.
So we have like an
Direction.
angular coordinate, but you have many cells.
Mm.
So
And
you get, point cloud data in a
yeah,
high dimensional space.
yeah,
And here you're checking not if it's on the surface of a sphere, but if it lies on a ring,
in the circle, yeah, exactly,
on
in
a
the ring,
circle,
exactly,
right?
yeah,
And so again,
yeah,
this is like a perfect thing. I mean, this is like an
mm.
obvious example, right? To try to
Mm.
check if the topological tools will pick up that circle.
Mm. Exactly,
Um,
and then you had also this paper from Trondheim, I guess, with
yeah,
Benjamin Dunn, who
yeah,
did analysis, and the
from the
Mosers,
Moser
who did
lab
the data.
data,
Yeah, yeah.
exactly.
So that was
Yeah.
really cool because there's so a
Hmm.
toroid, right?
Yeah. So that paper is very cool. So that's the
Yeah,
Nature paper from I guess it's 2 years old now or something,
2022 or
2021
something. Yeah.
or
So which
2022. Yeah.
actually found all these. Yeah. So I guess the key thing there was to have actually enough cells. That is sort of
Yeah. So
yeah.
they were looking at grid cells, right?
Mm,
And the grid cells are make a different prediction from place cells,
mm,
right? So with the grid cells, because of the grid-like structure of the fields, what you and the repetition of them, what you
mm,
actually expect is a torus,
yeah.
irrespective of the environment,
Mm,
right?
yeah.
And so when they manage to record many cells. The tricky thing is you have to record cells that are in the same kind of module.
Okay. Yeah.
So
Because they have different
right,
distances between.
there are different tori,
Yeah.
right? So there are
Yeah.
like there are
Mm,
the spacing and the orientation of the
mm,
fundamental domain for the grid cells
mm.
varies, and so you have to group them together.
But
Um,
how? I mean, if you sort of think of it from like if you think of these grid cells, right? They have what's called they have periodic boundary conditions, as we would say in
yeah, this
physics, right?
hexagonal. They have these
Yeah.
hexagonal
Yeah,
grid-like
and then
patterns.
and if it curls up, it's sort of if you sort of just if it curls up to like the essentially curling up a chessboard, right? Or with a triangle
Yeah, I
grid,
mean
it
it's
ends up with a
hexagonal, so
torus, right?
it's not quite the
No,
yeah.
but it ends up
It's
with some kind of torus just from
in
the.
the end, yeah,
So
you can predict that it should be a
yeah,
torus.
so would it be? I mean, would it even be conceivable that it's not torus? I mean,
So here's
what? Yeah.
yeah, so here's the thing, right? So everyone who had thought about it, right,
Mm,
expected to see a torus
mm,
for grid cells in the open field where you
mm,
see the hexagonal structure.
yeah.
Because from the hexagonal structure itself, right, you can see the way that there's like a fundamental domain, and you can see the way that
Sort of.
things get identified, that the boundary gets identified. It
Mm,
really patches up into a torus. So you really
yeah.
should see a torus.
Mm,
Um, and so that was predicted. I think I even mentioned it in a review article I wrote,
mm,
like in
mm,
2016 or 2017, um, that it should be a torus. But I was not the only one. Like, I
no.
think everybody who had thought about it expected a torus in
Mm,
that condition. Okay.
yeah.
Now, what was not known is what would happen when the animal was in different kinds of environments.
Mm,
So one of the
yeah.
cool things that they did, in addition to like recording like 10,000 neurons,
Mm,
um, is they looked at neurons in different kinds of environments. So one of them was like a wheel wagon environment.
mm,
So it was so there was like a circular track with connections crossing.
mm,
Okay, that had like four holes.
yeah.
Right. So if I look at place cells in this environment, I actually expect to see those four holes.
Mm,
Right.
yeah.
But the grid cells, um, they don't care.
Okay.
Always give you a torus
Okay. Yeah.
when the animal
Exactly.
is sleeping, and so they're always giving you a torus. And that was,
Yeah.
I think, one of the remarkable things that they found was that the torus is really in the structure of the network.
Yeah.
It's not just being inherited by
Oh,
the grid fields, and the
I
grid
see.
fields are come it's really the network is organized in this way, and
Mm,
so no matter where you put the animal, the
mm,
grid cells are going to give you a torus.
cool. Yeah.
Yeah,
Mm.
yeah.
We actually have a sort of a paper from our group. We have an excellent PhD student, Kostya Beshko. So I looked at this
Uh-huh.
for like using some data from Janili Farm, where they see this, at least with this from primary visual cortex, where you also see
And the
this.
fly paper, right?
No, this
There's
is not the
yeah,
fly. This is
oh,
actually
it's not the fly.
the mouse. That's a mouse
Okay,
data, but it
okay.
sort of also has this because of this. You have this orientation selective cell and direction selective cells. You get
Uh-huh,
these sort of different like
uh-huh,
circular manifolds and so on.
uh-huh.
So that's sort of
Yeah, I think the circle has been seen a couple of times, right?
yeah,
There's another paper from Janelia from Vivek Jay. I never get his last name right.
yeah,
Jayarama.
You think
But
about the fly thing?
the fly,
Yeah, that's a beautiful.
yeah,
Yeah. Mm.
that's a very nice. Anyway, so
So
these. Mhm.
yeah, cool. So now this was. I'm very impressed by your pedagogical skills, right? I mean, to talk about the topology on the radio, it's not. That's not for
Not
beginners.
that easy, right? I'm like
Yeah.
trying to use my hands a lot.
No, actually, we have this. In Norway, we give out this Abel Prize for mathematics,
Yeah, yeah,
and
I
which is
know.
sort of cool. Yeah, and then whenever spring there is sort of like the winner is advertised, and I know a friend of mine is a professor in mathematics, so he often is called to the radio to talk about what kind of
About what
significance
it is.
the work has for society, which
Yeah,
is often a challenge.
a difficult task. Yes.
Yeah, but I think so. I have very respect for sort of trying to popularize like mathematics. That yeah, but it's but yeah, oh, it's cool. So, but I mean, now we're going to change a little bit gear because I remember I think we were in contact after you were sort of invited on a podcast, sort of called Brain Inspired.
Brain inspired. Yes.
Yeah, with an excellent podcast.
And I said upsetting things. I
No,
think.
no, not really. You said something about beautiful models and ugly models, and I
Mm-hmm.
realized when I heard all of that this, like, sort of, I mean, this, I mean, if you do like the kind of work that we have been doing, sort of like looking at this very like large scale network models with biophysical detailed neuron models and so on. Of course, they are sort of it's something we call disparagingly physics for number crunching. It was
Yeah.
we
Yeah.
this is
I
sort of
didn't. Yeah.
yeah,
I
but I mean
didn't.
it's I think there's but then yeah, but of course and they could be maybe called yeah, so but you sort of we had the opposite, the beautiful models. So I think we certainly agree on beautiful models. So what is for you a beautiful? I think the background was that you had been on some kind of meeting when this brain project started in the US, and you
Yeah.
were
The
a little
Obama
bit
brain
worried that all focus was going to be on this sort of like ugly models or complex models, right? So you thought there should be a little some room for
Yeah,
the
I
more
think.
principled. Yeah, please, yeah,
I mean,
please,
I do have a lot of. I mean, I do have great respect for trying to like
yeah,
actually do detailed models. I
mm,
think that's and large scale models. I do think that's important.
mm,
I think yeah, I think what I was trying to say is I hoped at the time, and I still hope, and I think I'm
mm,
sort of optimistic about it that there's a little bit of space carved out,
yeah,
right, for trying to tackle. Um, I guess what I call beautiful models, but what I really
mm,
mean are models that are rich enough to capture some
mm.
aspects, right, of neural dynamics, but simple enough that you can actually analyze them
Mm.
mathematically and maybe prove theorems about them.
Yeah. No, I think you should be more. I think we should not only a small piece carved out. I think big piece. I think sort of like this simpler models, more principal models, is certainly a very important part
Mm.
of computational neuroscience. So I certainly agree with you that there should be room for like simple models. And I guess the most beautiful model, or one of the most beautiful model, is the Hopfield model.
Hmm.
So because
Absolutely.
you have worked a little bit in the extension of that, so
Yep.
I would say, so what is maybe you can just before
Hmm.
as a warm up for that, just tell about the Hopfield model, which came in the early
Yeah.
'80s, I guess.
Yeah, early 80s, late
Mm,
70s, something like that. Yeah, so the Hopfield model is a kind of a standard example, I think, or maybe the standard example of a beautiful model. Um, and it's an extremely simplified network model. So your neurons are points,
mm,
right? The interactions are given by weights, just simple real numbers. And so you have a weight matrix W,
mm,
and your neurons are either on or off. So they're kind of the earliest instantiation, I think, is just binary neurons, although there are later versions. There are many versions of the Hopfield model. So I'm just going to sort of
mm,
talk about the initial one. And so the neurons are, 0 or 1, or in some versions it's plus or minus 1.
mm. Yeah.
And and then you have this very simple interaction. So at every time step, right, you look at a neuron, you sum the weight, you take a weighted sum of its neighbors, you check it against some threshold, right? And if it's above the threshold, your neuron fires the next time step, or it's at 1 the next time step. And if not, then it's at 0 the next time step. And you just keep going like this. And so you have a nonlinear dynamical system that evolves in time. Is very simple, but it has a couple of nice features, which is why I think so many neuroscientists, or so many, theoretical and computational neuroscientists fell in love with it originally, is that it exhibits, it's kind of the simplest example that exhibits the so-called attractor dynamics, right? So these are nonlinear enough that you get attractors, and in the attractors in the Hopfield model are stable fixed points. So basically, you start with some initial condition. The initial condition is a configuration of firing, like these neurons are on, the rest are off. That's your initial condition. And you can think of that as a response to a stimulus, right? The stimulus comes, it activates some subset of neurons, the rest are silent. And then you start evolving the network according to this rule, right? And the way that it evolves is completely determined by the weight matrix. So you have recurrent connections between the neurons, and the weight matrix dictates the evolution of this network. And then it will stabilize, right, at a fixed point. And a fixed point means some pattern of neurons that are on and the rest are off. And then as you keep going forward in time, that pattern stays the same. So when you keep evolving, like, you get no change. And so this was a very, I think, beautiful model of the way that a recurrent network could take an input and transform it into an output that was dictated or encoded by the synaptic weights. And at the at the time that this model was developed, this idea of long-term memory, right, long-term potentiation and long-term depression of synapses was being kind of actively investigated. Ideas going back to, say, Donald Hebb, and the idea that neurons that fire together wire together. And so the question was, all right, suppose you had a network that had been trained, right, that had learned weights, where neurons had sort of been wired up according to prior experience. What would it do, right? And so what it would do is it would encode memory patterns. And you can do simple examples where you think of your neurons as reflecting pixel values on an image, right? So you can think of black and white image. When the neuron is on, it reflects the white value. When it's off, it reflects the black value, for example. And you can feed a network that's been trained properly, that has a good weight matrix for this. You can feed it a corrupted image. And as this dynamical system evolves the activity forward, it falls into the stable fixed point, which is the clean, noise-free image that's been stored. And so you have this idea of, like, okay, the memory pattern, which is the image, is stored in this network because there is a stable fixed point of the network that corresponds to this pattern. And if I start nearby in the basin of attraction, right, of the stable fixed point, then the network will clean up the image for me.
And I guess they also had this nice argument that this energy function, that it was always going to,
Right.
that each step you're going to get closer to this,
Right.
the bottom of the attractor, sort of.
Right. So
To
there's
the
this
pure
question
image.
of, like, can I guarantee, I mean, I've set up this dynamical system. I have this rule to go from one time step to the next. Can I guarantee that I'm actually going to stabilize somewhere? Right. So people were worried about that. And so, so Hopfield, proved this result. I think he actually called it a theorem.
Yeah.
He's a physicist.
He wanted to be a mathematician.
Right. He proved this result
Yeah.
in the PNAS paper in, like, 1982 or something, right? That if the weight matrix were symmetric, right, then you are guaranteed to converge. No matter what your initial condition is, you're guaranteed to converge to one of these stable fixed points. And so the network isn't just going to, like, endlessly wander around trying to find the output. It will actually converge to something. And the way that he proved it was by writing down an energy function, which in dynamical systems lingo would be a Lyapunov function that decreases along trajectories. And so then you can show that you're always going to make progress towards one of these stable fixed points.
So this is clearly an example of a very beautiful and also obviously very useful model, which has inspired a lot of
Has inspired a lot.
ideas and things.
Yeah. And also very wrong in many ways. Right?
Yeah.
So the binary nature of the neurons, the simplified weights, and the symmetry assumption, right? The idea that the connections are symmetric, all of that is is clearly wrong, and yet the model still captures this notion of memories can be stored in a
Mm.
network via the synaptic weights. I think that
Yeah.
was kind of the key idea that is really
Mm.
nicely
I actually
implemented.
was one of my first when I switched to neuroscience or started in neuroscience. I was at the meeting in Sweden where he was.
Mhm,
So I asked
mhm,
him what kind of role did he think his sort of his network model would have, right? And or this Hopfield network, and he said
mhm.
it might be a metaphor. He said for how the memory works, and that's certainly.
Yeah,
Another
I
thing
think
he said was actually, I remember he started his talk saying that in computational neuroscience, we have to learn to compute without knowing all the numbers, and that's very difficult. So
yeah,
that's which is true. So that's what we're struggling with.
right.
But this networks, of course, what was like, from a mathematical point of view, it had a very simple dynamics, and what made the
Mhm,
trouble was sort of it was like a simple, well, ordinary differential equations with a decay term, like
mhm.
dxt is minus x, and then plus a source term, and this source term was had like this step function like behavior, right, or step function like. So
Yeah, so
that was like
that's
the
the other. The nonlinearity is like a heavy side step
yeah
function.
heavy side exactly.
Yeah,
And
in the
then, but
original.
yeah,
So
original. But then it was, as I said, it was sort of extended to this what's called, I guess now we call the ReLU units, right? It's like this what's called linear threshold,
linear
and
threshold.
so a lot of this work was then, or the Hopfield idea was also explored in
Mhm.
this kind of
Yeah, I mean, it was in a few ways. So the Hopfield idea. So I should also say, I mean, around the same time. So Hopfield had a very influential paper that gets cited a lot from '82, around the same time, or even a few years earlier, right? So there's papers by like Cohen and Grossberg, who were mathematicians
mm,
who proved similar theorems, maybe stronger theorems that had kind of embodied wider range of nonlinearities and a wider, like, had fewer assumptions.
mm,
Um, in a way, the Hopfield paper, I think, was more popular because it was more limited, right?
mm,
And so sometimes when you see a result that's like more specific and not in full generality, it's
mm.
easier to understand and
Yeah.
appreciate. So it's like but I would say this idea was kind of like in the air more broadly, and as a mathematician, I should give credit to people in the math community as well. We're thinking
Mm,
about this in the
mm,
dynamical systems kind of language.
mm.
But then, yeah, so then later you know, a lot was done with Hopfield networks. Um, I think in the '80s there was kind of an explosion of activity. Lots of physicists, particularly physicists from statistical mechanics. Is that your background, or were you one of the stat
Yeah,
back?
I was doing a little bit statistical physics, but also more like condensed matter physics, like
Okay.
semiconductor
Like
physics.
this is the more typical background, if I
That's
feel,
true.
for
Yeah,
physicists coming into neuroscience. So
spin
I think the
glasses.
Hopfield model
Mm,
was extremely appealing
mm,
to those kinds of physicists,
mm,
but even more broadly. And then, yeah, so I say later, like starting more in the '90s or late '90s, right? So um, other kinds of rate models became popular, firing rate models, and some that are similar to Hopfield in the sense of encoding memory patterns by stable fixed points. So the ones that really inspired me, which I think is what you're getting to, are the
mm,
threshold linear networks. And yeah, so these are a lot like the Hopfield model, except it's like a continuous um, rate value for each neuron. It's like a firing rate for each neuron instead of just a binary, it's on or it's off. It actually has a rate. And then the nonlinearity is the ReLU, what the
mm,
machine learning people call ReLU.
mm.
Um,
So it's like 0 up to a threshold, and then it
yeah,
linearly, and then
right.
it's
So below a threshold is 0. Beyond the threshold, it's just a linear increasing function.
mm. Yeah.
Hmm.
And that, so then they found, so what was the outcome of these studies? They found that like for these symmetric connections, you still had like, did it change much compared to the Hopfield results?
Right. So I think these networks started getting used to model, in modeling, right? So to model hippocampal function and so on as associative memory networks, as a version of Hopfield that was maybe a little more realistic. And then um, there was a group, Sebastian Sung and Hanlaser and Slotine, and maybe some others in around 2000, right? So about 24 years ago, they had a series of papers on what they called permitted and forbidden sets.
Mm-hmm.
And one of the papers that's particularly nice is from 2003, called Permitted and Forbidden Sets in Symmetric Threshold Linear Networks, something like this. It's a paper I cite a lot in my own
Okay.
work, because it very much inspired me and my collaborators. And in this paper, they consider the symmetric case
Mm-hmm.
and inhibitory networks. So the the interaction matrix is all
Mm-hmm.
negative values, so it's like effective inhibition.
Mm-hmm.
um, and they prove a result that's completely analogous to the Hopfield energy function result. So in other words, they write down also a Lyapunov, well, they call it a Lyapunov-like function because it doesn't
Mm-hmm.
quite satisfy all the conditions of a traditional Lyapunov function, but it's like an energy function
Mm-hmm.
that decreases, and they show that it decreases along trajectories. And so they're able to also show that these networks, under some mild conditions, um, are guaranteed to converge to stable fixed points, and therefore can serve as networks that encode memory patterns in the same
So
way.
you're saying all inhibition, all inhibitor, but what makes them fire then? I mean, there must be
Oh, you have an
some
external, yeah, you have an
external.
external drive. Yeah. And
Exactly, that
this was
lifts
true of
everything.
many of the models
Mm.
when these were used in modeling. It's like you imagine a constant drive to all the
Mm.
neurons. So you're thinking
Mm-hmm.
of this as a model of a recurrent network that's receiving input
Mm-hmm.
from another layer or from stimuli or something. And so there's a lot of inhibition in the recurrent network, but it's getting this external drive. And so
Mm.
basically the external drive is kind of activating the network, but then the inhibition is
Uh-huh.
selecting.
Yeah.
It's a generalization on a winner take all
Mm.
kind of
Mm.
network. So
Yeah.
the inhibition is selecting
Mm.
who gets to fire.
Yeah. And then you took the bold step to look at asymmetric weights, right?
Yes.
And then
Yeah.
what's it, all hell
And then
breaks
all
loose.
hell breaks loose.
Yeah.
Yeah.
Okay. So
So
then it's yeah, that it takes a bold woman to do this.
yeah, I guess so.
Yeah.
And my collaborators,
Okay.
most
Good.
of whom are women, actually. But yeah, for real. Um, but yeah. So initially, I should say, initially, I was not so bold. So initially, around 2009, I was a postdoc actually at NYU. Now I had moved from Ken's lab to a position in the NYU math department, Current Institute, mainly because I had a baby.
Yeah.
I was like, and I was living in New York City, and I
So
had to
you
like
so you
cut down on my commute.
you can't have babies at Rutgers. Is
No, it's just I was living on the Upper West Side,
Oh, I see. Yeah.
and it was just like very long commute, so it was much
Yeah.
shorter to go
Yeah.
anyway. So
Yeah.
I went back to math department, but at NYU, where there were many
Mm.
people in the math department interested in neuroscience, so it was a good fit. Um, but around that time, so I was at NYU. Vladimir Itzkov was at Columbia, working in the Center for Theoretical Neuroscience with Larry Abbott and Ken Miller and those guys.
Mm.
And we came across this paper. So we had done our topology thing from
Mm.
2008, right? But then we got
Mm.
interested in this permitted and forbidden sets paper from years before. I mean, at that time it was like, I don't know, 7 or 8 years old, and just kind of fell in love with the idea that you could prove. So they prove theorems in
Mm.
that paper, right?
Mm.
And
Yeah.
it was like, oh, you can prove theorems about this more,
Yeah.
kind of more realistic version of the Hopfield model. And the reason you can prove theorems is because these networks are actually piecewise linear.
Mm.
So they're
Yeah.
not, have this nonlinearity, but locally they're linear, and they just have like different linear systems that
Mm.
are all interacting with each other.
Yeah.
And so that was just like, it was a very lovely setup, right? And so then we collaborated with a friend of mine from grad school who's a straight up mathematician. She's actually a differential geometer, Anda Degeratu. So her name is on some of the earlier papers. And we started trying to think about the collection of stable fixed points.
Mm.
So I would say the Sung and Slotin and Honlosser papers were about which subsets of neurons could possibly give you a stable fixed point under some input vector.
Mm.
Okay. And then we started thinking, well, if you fix the input, what's the full collection of stable fixed points that you get? Right. So what's the code? What's the
Mm.
full neural code? So we were thinking neural code thoughts, right? So it's like,
Mm.
can we implement a neural code that has a nice structure like the hippocampal place field
So,
code.
but what's the? I mean, fixed points is not the same as neural code, right? I mean,
Well, so every fixed point is characterized by a support, which is the subset of neurons active at it. So it's like I have a
okay.
fixed point in my dynamical system in my sort of n-dimensional state space, but
Mm,
that fixed point is characterized by certain neurons being on
mm,
and the rest being off.
yep.
Okay.
Huh?
And so, in fact, in these threshold linear networks, that completely characterizes the fixed points, which ones are on and which ones are off, even though they have
Mm,
different firing rates.
mm,
Once
huh?
you select a subset of neurons, you can work out what the fixed point should be. So
Okay.
the whole game is like which subsets.
Yeah. Mm,
Okay, and so a subset of neurons that supports a fixed point, you could think of as a binary code word.
yeah, that's true. Like a
Okay, so this is like
memory.
right. So it's like I imagine maybe that set of neurons corresponds to some place cells with overlapping place fields,
Mm,
and that code word, which has ones where those uh, for those neurons and zeros for the others are representing that position where the
huh?
place fields overlap. Okay,
Mm,
so yeah, so you can take the set of stable fixed points, and for each stable fixed point, just record kind of the binary who's on and who's off, and you get a neural code.
mm,
And so
mm,
we got interested in this question of what neural codes can be encoded, and there's certain structures that can be encoded nicely, and others that cannot. And so we went down the rabbit hole with symmetric matrices for a
mm.
while. So we like fully like
Yeah.
plunged into that, and all still with the symmetric matrices because they're your guaranteed stable fixed points, right? And then we kind of got bored with that, and
Mm,
then it was like, okay, what if we forbid stable fixed points? Right? What if we go the opposite extreme and look at
mm,
networks where there's no stable fixed points?
mm,
So how do we do that, right?
mm,
Because actually, if you just make random networks, they're going to have stable fixed points.
I see.
So
Yeah.
this is where math really helped us,
Okay.
and there are some like linear algebra facts, really simple linear algebra facts that are like in our papers that we were able to prove that enabled us to very simply construct networks that had no stable fixed points, and they're asymmetric,
Yeah. But then
right?
you have some kind of other kind of attractors, right?
Right. And then you get other kinds of attractors.
Yeah.
So that's the beauty of it, right? When
Yeah.
you go to the asymmetric case and kind of get rid of the stable fixed points, you still get attractors because we were still kind of in this inhibition dominated regime. So we
Mm,
didn't get rid of that. We stayed like sort of inhibition dominated. And so the network has to do something, and it does fall into attractors, but instead of falling into these kind of boring attractors, just a stable fixed point, which is some
mm,
static pattern of like who's on and who's off. Instead, you get these limit cycles and chaotic
mm.
attractors and all these other interesting attractors. So it's still attractor dynamics,
Huh,
but it's no longer the static fixed points. Now
mm,
it's like you fall into like periodic patterns,
yeah.
oscillations.
Huh. I guess this has, I mean, I don't know much about this, but there are these ideas about these cortical songs and that you sort of have this, right? That
Yeah.
you follow these particular patterns, which are seen both like in background activity and in stimulus evoked activity, right? So there
Right,
seems to be
right. So
something like
I
this.
was very much enamored with these kinds of attractors because actually when I was, going back to my postdoc in Ken Harris's lab, what I looked at primarily in terms of the data was data from auditory cortex during sleep, during anesthesia, and during awake. And a lot of what I was doing as in my computational work was characterizing the ongoing patterns of activity and
Mm,
looking at the interaction between stimulus evoked and spontaneous activity
huh,
and just seeing these oscillations all the time. But there were
mm,
transitions, right? So you'd have some oscillatory pattern of activity, and then maybe we'd like pinch the tail of the animal or something, and there would
uh,
be some
huh,
neuromodulator like acetylcholine gets dumped into the cortex, and suddenly the pattern shifts, right?
mm,
And so this was a very familiar idea to me that you would have a pattern. You're not just wandering the state space randomly, right? You're not going to a stable fixed point, but you're also not random, right? You're
mm,
not ergodic or chaotic or whatever. The activity goes into fixed patterns and then switches into different patterns. And so that was kind of,
mm,
in the back of my mind as we were doing this work is like so lovely, right? That you can see that these networks would generate these
mm,
very stereotypical patterns of activity that are encoded in the weight matrix as
mm,
opposed to just the static fixed points.
mm.
Yeah.
Yeah. And
Yeah.
because you were able to, yeah, exactly. So then you saw that you get all kinds of, with this asymmetric connections, you got all kinds of weird cycles and attractors and
Yeah.
stuff. And
Yeah.
then, then you were able to to prove some things again with this
Right.
subclass,
Right.
right? With this what's
Right.
called combinatorial
Right. The
threshold. Yeah,
combinatorial threshold.
yeah.
Exactly. So,
So
I
that was
mean,
sort
it's
of
one
cool.
thing
Yeah,
to, I mean, so, you can set up a lot of dynamical systems that produce
yeah,
crazy activity, right? So
yeah,
it's like, it was fun to see that, right?
yeah.
But that's not really
Uh,
enough to make it worth studying.
no.
And so what really, really captured my imagination was uh, being able to predict these patterns,
Mm,
right? And so this is when I started working with Katie Morrison,
mm,
who was someone I worked with before on neural code stuff. So she had been a graduate student in Nebraska. I spent 5 years in Nebraska a long time ago.
oh,
My first tenure track job was at the
okay.
University of Nebraska before I came to Penn State.
Mm,
And there had been a coding theorist there, Judy Walker, and one of her students, Katie Morrison. Initially, we were just working on neural code stuff. So we wrote some
mm,
paper on
mm,
combinatorial neural codes. And then she went off to a tenure track position at University of Northern Colorado, but we kept
mm,
in touch. And at some point, she came to visit me at Penn State, and I showed her these
mm,
graphs. I was like, well, we can make these threshold linear networks a subfamily based on a graph structure,
mm,
right? And so then the graphs were a way of keeping track of weak versus strong inhibition. So they were
mm,
inhibitory networks. They had this like winner take all kind of behavior, but depending on the pattern of weak and strong inhibition, you'd get different patterns of activity.
huh,
And so the cool thing about the combinatorial threshold linear networks is they're a subfamily where where every network is sort of dictated by a graph and just a couple of parameters. We have like this epsilon and delta, which tells you how much
mm,
above the leak term is your weak inhibition and how much below the leak term is your strong inhibition in
mm,
terms of the synaptic weight. And so the game, right, which like she was, very interested in helping me pursue. And so we've been working on this for like 10 years now at this point, but like,
no,
or 8 years
mm,
or something. The game was then to um, try to connect the graph structure to the dynamics.
mm.
Can
Yeah,
we analyze that graph, right? Look for, sources, sinks, different cycles. Can we look at sort of combinatorial features of that graph and then make predictions about the attractors?
yeah, mm,
That was the game. And
mm,
yeah, and I guess the reason I'm talking to you about this is because we could.
yeah,
We could do a lot, right?
yeah,
And even though we had all this crazy limit cycles and all these different kinds of
mm,
attractors, we can actually predict their existence and predict for many of them we can predict um, their shape. Like we have this work on sequential attractors where we can look at the graph and say, oh, this attractor is going to have these sequences.
mm,
I was very interested in sequences as well because from my days looking at hippocampal data, right, that was a big thing.
mm,
When I was a postdoc, was sort of looking at neural sequences, right,
huh,
like sequences of
yeah,
activity, and so these attractors would like have the neurons fire
mm,
in these different sequences, and we spent a lot of time trying to predict the sequence as
yeah.
well.
One nice feature I saw also that you had some theorems for, if you have like these network motifs, when are they going to be destroyed by external input, or when are they going to be some sense strong enough to sort of
Right.
to survive even in a embedded
Survive.
in a
Yeah.
larger network? That was very nice.
Right, right. So that was
That's
another thing is like you can have a subnetwork, right, that
mm,
has a certain pattern of activity. So it's like in isolation, if it's only those 10 neurons or whatever,
mm,
right, they have some pattern. But now you embed that in a larger network,
huh,
right? And the question is, will that limit cycle or will that attractor
mm,
survive in the larger network? And
huh,
so, yeah, so we were able to prove theorems about that too,
yeah,
which is really fun.
yeah.
So, yeah, so
Which
I mean, yeah, so
makes yeah, cool.
mathematically is a very fun playground, but it also, I think, um,
But I mean, I'm sort of
has a-
from my point of view, these are also very useful things to get some ideas. Sort of when you look at the
Mhm.
network, you want some kind of ways to think about this, like a preliminary way to think about things that you can sort of then explore in like more complicated models, right? So I mean, it's
Yeah, I do view it as like I mean, I view a lot of the more mathematical theoretical neuroscience. I view it as kind of developing the imagination, right, for what
Mm.
kinds of things can happen, right, or
Yeah.
what. And so I think what these models show, right, is that in the same way that you can have um, the weight matrix of a network can
Mm.
encode fixed point attractors, right? It can also encode dynamic attractors, which may be reflecting central pattern generator circuits or
Mm.
other kinds of rhythmic behavior. And then also, in the model, right, you can actually start to tease apart which weights matter, which don't matter. A lot of
Mm.
what I've been interested in lately is sort of thinking about, once I have an attractor that's stored,
Yeah.
right? Some kind of, periodic pattern of activity, and maybe it's like a memory of a song or something, and a metaphor for that anyhow,
Mm.
right? Once I have an attractor stored, can I, which weights do I have to freeze, and
Mm.
which weights can I alter
Mm.
to have the network learn other attractors without
Mm.
affecting the initial one,
Yeah.
right? So this is a more challenging problem than in the case of stable fixed points, because now the attractor itself has a structure,
Mm.
right?
Yeah.
And it has this dynamic structure that you don't want to screw up,
Mm.
right?
Yeah.
So it's like you want to keep that rhythm, but add other things to the network. And so in the model, we can actually address those questions, and we can think about, like, which weights are plastic are still
Mm.
flexible and which weights need to be frozen, and so on. And it just gives ideas, I think,
Yeah.
for how the brain may be able to, like,
Mm.
store new memories that are more complicated, right?
Yeah.
Patterns without.
And because you also, I saw that you had some that this kind of approaches and your modeling approach could also address some of this, like this question of central pattern generators, that you could
Mhm,
actually
mhm,
get this different gates and whatever, this kind of
right,
weird like ways that horses can run uh,
right,
with the same network just by changing some initial conditions.
right,
Yeah.
right. So that was one of the things that we did with my graduate student Juliana,
Mm.
London Alvarez. So we, put it as a challenge, right? So this is like, if you look at a mathematical neuroscience textbook, right? So there are these um, coupled oscillator models that encode gates, but there's
Yeah.
usually some parameter you have to change, right? You need
Mm.
synaptic plasticity or something to transition from one pattern of activity to another.
Mm.
And so our question was like, okay, can we encode these gates, right? So
Mm.
different patterns of locomotion for a horse, say,
Mm.
just to give an
Yeah.
example that has some interesting variety. Can we encode them in the same network where we're using the same neurons? The same
Yeah.
neurons have to be engaged in different patterns. So there's like lots of overlap, right? In
Mm.
terms of which neurons are engaged in the attractor. Can we do it in a way that, like, we don't have to change the network? Like
Mm.
the synapses are the same. It's just initial conditions that transition you from one to the other.
Mm.
And that,
Yeah.
I didn't know if it was possible
No.
initially, because the existing models really do require changing parameters.
Mm.
But yeah, with the CTLNs, with these combinatorial threshold linear networks, it was,
Mm.
and with the level of understanding that we had about the limit cycles and how they would be preserved, it was not that hard.
No.
And so that was kind of one of
Interesting.
the things that felt really right about the modeling framework.
Because in a recent podcast we had with Henrik Lindén, he has sort of been we worked in Copenhagen on like the central pattern generators in turtle. So,
Oh
but then
yeah.
he also has a whole, I say this in the lab of Runeberg. So he had this sort of like all of this. Well, it was a firing rate model, but
Hmm.
one of the things that they also found was that they could get these different gate patterns in their model, but they could also speed up the
Hmm.
oscillations by changing the gain, I guess, of some of these
Hmm.
neurons and stuff. So that was
Hmm.
also a way to sort of, if you're a horse, but
Yep.
not want to change the gait, you just want to do it
Want to
run
speed it
faster.
up.
Yeah. So
Yep.
that's sort of interesting. So which sort of that you can actually, but it's sort of like, I guess
Hmm.
your work also illustrates his point, or the point from his work is that sort of with like simple network, neuron units, like the network dynamics can actually arrange a lot of this.
Right.
Can a lot of variety. You don't need particular
Right.
sort of like pacemaker neurons or something.
Exactly.
Yeah.
Exactly. So I think that is absolutely one of the things that my work, my modeling
Hmm.
also shows, right? You don't need pacemaker neurons. You don't need neurons that have intrinsic oscillations, right? The
Yeah.
oscillation can be an emergent property of the network itself.
Oh, the cat is coming. Oh, this is what you. so are going to join us. So
Uh,
we're almost done. So, but one thing, one general question. I mean, your work here, which I think is really nice and illuminating. But it's been on. I mean, it's on using firing rate models. How
mhm,
much do you? How much do you think this? Okay, I mean, of course, while real neurons are firing spikes.
mhm.
So how do you think this generalize, or how different are they, or yeah, sort of how much do we miss?
Yeah. I mean, I think it's known that rate models miss a lot. I
Mm,
think that is definitely. I mean, rate models in general, right? They're used
mm,
in a lot of theoretical neuroscience, and there are features that spiking models get that
mm,
rate models are
okay.
fundamentally limited on, right? But in some cases, it has. People have shown um, that the rate model can be a good approximation to some features of a spiking model, right? And
Yeah.
so I don't have too much to say beyond that, except
Mm,
that in the case, so one of the things that I haven't thought very deeply about connecting these particular rate models to spiking models. I mean, I think other people are working on that, um and I'm not using like different rate models than what's sort of the standard, right? So these are standard. So whatever results apply there, should apply to the TLNs as
okay.
well. So I've kind of, left left that as as
Mm,
other people who are sort of more specialists in the spiking models. But on the
mm,
other hand, um, uh, one of the things that I was sort of optimistic about is so I have this collaboration with the zebrafish physiologist in Paris, Herman Sumbre, right? So he collects calcium imaging data from the optic tectum of zebrafish larvae, and so we've been using some of these ideas to try to model. We have a lot of like work being written up right now, I have to say, so I can't point you
mm,
to any paper yet. Um, and uh, One of his collaborators um, got interested in the CTLNs, and he's a physicist,
yeah,
Marcelo
the
Rosenberg.
CTLNs. That's your
That's a
specialized,
special
yeah,
case,
a
right?
special case of the threshold
A
linear. Yeah.
special case of the threshold linear network. So he got interested
Mm,
in the CTLNs because he was trying to build simple neural networks in hardware, spiking
mm,
networks in hardware. So he's a physicist, so he wanted to actually, make a circuit, right, that
mm,
would implement the kind of uh, spiking dynamics. Okay,
mm,
and he got interested in the CTLNs and wanted to try. He was just like, try making a network that would respect the same graph structure,
mm,
right? So it's like, okay, so you have some graph structure, and in the CTLN, I can tell you the dynamics are going to look like this. I have theorems, I have
mm,
simulations, and I can say, well, if your network structure has this pattern, these two neurons will synchronize, and then they'll fire in some, you
okay.
know, sequential pattern with these other neurons, and so on. So I can tell you a lot in the firing
Mm,
rate model. Um, Now, what happens if you take the same graph structure, right, and implement it just in an electric circuit that's meant to mimic spiking with spikes? Okay. And so he did some preliminary work, and now there's going to be a lot more because he just got a grant to pursue this further. But it was actually extremely well predicted. So he saw spiking activity in the same sequences that we
okay.
predicted from the firing rate model in
Mm,
these simple cases. And so there's something, I feel like there's something kind of universal about that graph structure, right? So it's
mm,
like if you have a competitive network where the neurons are in competition with each other, so they kind of want to fire in sequences, and the graph structure is really capturing weak versus strong inhibition,
mm,
right? Then it seems like that graph structure can be imported into, I mean, in the case of threshold linear networks, I can tell you a lot. I can write this simple dynamical system. I put equations on the graph, right?
mm,
I put the system of differential equations, the ODE for the TLNs, and I can tell you a lot. But some of the lessons in terms of what the dynamics look like seem to carry out over into other types of
mm,
equations, right?
mm,
So in
okay.
his spiking model, it was a very different set of equations. I've also seen what are called like species competition models. So this is
Mm,
now from like population biology, okay?
mm,
So ecology, totally different field,
Mm.
where there are these models of like non-hierarchical species competition. Okay, so there's work by Alicina and others, and here what you have is you have pairs of species, and the graph is telling you, the sort of arrow of the graph is telling you this species dominates this species,
I
like a
see.
fox and a rabbit, like
Yeah,
literally
yeah,
like
yeah.
like different
Uh-huh.
creatures, right?
Yeah.
And they have these species competition graphs. I came across one of these papers many years
Mm.
ago, and it's like they had a graph on 5 nodes, very similar to one of the graphs that I had analyzed. And I
Mm.
just thought, okay, let me just take that graph and look at it, as a CTLM graph,
Mm.
as a threshold in your network. And I got exactly the same
Mm.
dynamics. Like they got a
Mm.
limit cycle, like periodic species population curves. Um,
Mm.
and we got exactly the same dynamics, even though their model was a probabilistic model. At every time step, you take a pair of species at random, whichever one is dominant captures the population of the other one. It was a completely different, it was a discrete probabilistic species competition model with the same graph.
I see.
And the
Because
dynamics were
yeah,
extremely similar. So
because I
there's
was thinking that, I mean, one question is sort of, if you sort of look at your CTLN models, if the unit in that model, neural unit, more is actually representing a population of neurons
population. Yeah.
rather than a single neuron. Because I mean, there are, if you see some of these population dynamics that
Hmm.
has been seen like and extracted in, well, from experiments and so on, it seems like the equations that describe them are sort of, actually you sometimes even get some like these ReLU like activation functions, and so maybe it's
Yeah.
maybe that's also a useful way to think about it in some
Yeah.
cases.
Yeah. I think that's true.
Yeah.
I think that's true. So anyway, so I view these again as in the same way that the Hopfield is maybe a metaphor, right? Like I would say the
Mm.
same thing about these models,
Mm.
in that I think they're capturing something, right, about like the competition dynamics. I
Mm.
think that's really what they capture. This sort of when you have competition between units or populations or
Mm.
whatever, and that's then you can see all this interesting kinds of dynamic structures, and this is what's I think captured in this particular instantiation of the competition graph, right? We can prove theorems, we can have a lot of
Mm.
detail, but I think some of
Yeah.
the flavor of those results does extend,
Mm. Yeah.
hopefully, I mean, in some cases for sure, and in other cases we
Yeah.
don't know.
Cool. Well, this has really been a pleasure, and I'm really, I can happy to see that like that you have sort of be able to bring all your skills from mathematics to such good use in neuroscience. So that's I think an inspiration for many people who are listening. So there are many ways to be useful. There are many skill sets that can be very useful in neuroscience. Yeah.
Mhm.
So I don't know if there's anything else that you should talk about before we hang up.
No, this has been
It's
fun.
it's
I
been
really appreciate that you do this.
yeah,
I think all everyone out there making podcasts and trying to
yeah,
um, bring the science more
yeah.
broad to more broad accessibility. I think
It's
that's great.
actually, but it's, I'm sort of a little bit surprised that it's not done more. I mean, one thing now, in like, if you look at sort of feel, I mean, like in terms of academic podcasts of this
Hmm.
type, which are sort of meant for the scientific community, there's not too many. Even in like, there's a lot of popular science podcasts, but
Hmm.
which are meant to general public, which is very nice. But that doesn't solve this kind of doesn't
Yeah,
solve this problem. So I think it's something that should be encouraged for many scientists, actually, in many fields, that they should have a vibrant field, should have like, they should have their own like specialized journals where they can publish their stuff, and they should have textbooks, and they should have meetings, and I also think they should have an academic podcast or two.
yeah.
So I think that's
No,
sort of
I agree.
yes,
I think it's
yeah.
great. So I
Hmm.
appreciate that you do this.
Well, I do it. Well, I, of course, I think it's useful, but I mainly do it because it's fun, and then I can sort of sit here and talk for 2 hours and 8 minutes with an expert, right?
So long. Did I
So
really talk that long? I'm sorry.
I know this. I'm just so,
Apologize.
no, this was wonderful. So I mean, this is sort of like picking the brains of experts. What can be better?
Hmm.
So that's one of the bonuses of making a podcast. Anyway, Carina, so thanks a lot. And then it was thanks a lot. And then I'm quite sure we'll meet at the conference within too
Someday.
long.
Yep.
Okay. So thanks a lot.
All right. Thank you. Bye.